PNP in short, right, as an abbreviation. Power and performance makes it a significant factor in this kind of products. So what would be the objective? What would we hope to achieve in this discussion? Right? First of all, the criticality of PNP will just demonstrate for a particular product milestone that typically companies work on, and this product would be a CPU as an example, or a GPU. We already know who work in these areas. So and some basics to actually set the kind of principles and basic principles and terminologies, right? So some can lead itself to research problems that we can actually think about working on. So leading to this from a quick review is an ecosystem for modeling estimation, right? So what we are trying to tell is that what are all the methods, tools, and techniques that I have at my disposal to basically go and model power and performance, estimate power and performance, all at the right time, at the right complexity, for the right product. And what is it that we tend to derive from verification, and how is it that it is actually important in the context of overall chip validation, and not necessarily verification as we think about it, but overall chip validation, how PNP is important. And I just want to demonstrate what is the role of ML techniques. Now, this is not something actually new in this sense, but because of the interest that has generated because of AI and ML. So we try to also look at how we can leverage those techniques to actually simplify or conquer the complexity of PNP. We end with some examples and open problems. So the last question is something that we wanted to brainstorm and keep it open. Can we have one framework for all silicon platforms? Is something that is an interesting problem to look at, and at least from the point of view of conquering the complexity. Okay? So this is a typical product development milestone. It's not actually tied to any company or any single product, but that's how it actually goes. And we easily recognize that there's always a pre-silicon phase where we have the design characterized, the circuit is architected, the system is architected, then it goes into a design phase, and eventually you identify what are the variants of the architecture. Let's take a CPU as an example in this case, right, for example. So what are the different SKUs, or the SKU, by SKU I mean a stock keeping unit. Let's say, for example, just to see what a kind of a same architecture goes into a laptop solution, a desktop solution, and eventually a high performance compute solution. So all these things have to be carefully addressed right at the beginning. And in this context, whereas we have all the challenges on the design, architecture, verification, there's also a power and performance vector to this. And that's what we are actually trying to highlight here. There is a need and necessity to keep a tab on the way the power and performance is going to turn up after our silicon, once we get back the silicon, and how we're going to do about it. So it will be too late. Obviously, we do chip validation for power and performance once the silicon comes back, but it's obviously too late to correct any problems that you have there, right? So there's a clear charter to have these checkpoints put at the right spots here in the product development milestone. But what is more interesting and more even challenging is that the pathfinding phase. And given that there are so many variants of AI solutions, applications being mapped onto different types of compute platforms, we need to know what is the right one to start with in the first instance. And the definition of a program execution in a company really depends on this pathfinding. And this is now out in open. It's not the same GPU having more frames per second, the CPU having more benchmark scores. It's no longer the same thing now. There's a wide matrix out in open where you need to optimize this and come up with the correct set of SKUs that goes to the right solution, that supports the right solution and goes to the right eventual platform. So the time for this is also dramatically shrinking, and really people want fast. The management wants the answers fast. Sometimes only 1 week. let me know if your new product meets a certain performance at power within just 1 week. So there's a lot of what if analysis goes back and forth here. And this is what we also want to really target. Right? We want to have a kind of long-term solution to this kind of problems, because it is not so easy, or it's not desirable for anybody to actually wait until the design is up and running to measure the power and performance, only to figure out that you're just not meeting the required spec. Well, it would have spent already some 6 months on this, and you will come to a point of no return when you actually come to this point. So what are the tools and techniques that actually enable us rapid pathfinding is something that we want to discuss today. And we will obviously touch upon the multiple checkpoints that we have mentioned here. It's very important as well. So, so this eventually, this gives a snapshot on what is the overall ecosystem. By ecosystem, I mean, what are all the tools, techniques, and what are all the methodologies that you have at your disposal to be able to define the right power and performance for a product. So just one quick word, I've been already using it. So it's not just the performance or the power that is important, it's the performance at power is the metric that's very important. The two things, the two boxes are very trivial and we all appreciate it, except that the fifth one, the regulatory reason, is also a very important one, right? So you go all the way, design a product, and eventually you find that you don't meet a California Energy Star rating, then you have a problem in the whole design. So that's the reason why power needs to be managed, and performance, obviously, we understand why it's going to be desirable enough, right? So it's all started. The interest in power and performance started long back, but it has now gone to a stage where without this, we are actually going to be running into serious problems. And these are some of the lessons that we have actually learned the hard way. Challenges in performance power is not a laundry list, it's the lessons that has been learned hard way. The power and performance is a make or break criteria, and that also means that we have to be able to validate at every stage of the design, starting from pathfinding. And it is imperative. So it's sort of, in the productivity sense, it's imperative to have well-established estimation and validation flow. Now, not all companies or not all tool vendors actually support this, but in some way, we need to have this kind of methodologies in place, and that's an active area of work for us. Because it's simple, fixes in silicon are not easy. We just have to throw silicon out. Even though it meets all your functional needs, it's not meeting your power and performance, you have to throw silicon out. The impact of power, and it's as a corollary, the impact on bill of materials is very significant. Right? You need to go and design your platform, for example. The board needs to be redesigned. It's all going to be very messy. It will cause the silicon to be coming back to the fabs. That is not a very desirable situation, being such a high-risk industry that the semiconductor industry is. So it's going to be very painful in terms of cost. So all it means is that it is critical to estimate, track, and validate the PNP at all stages. Again, this is the same statement that I'm making it again, but with one more important example. Right? There's always a risk of regressions. Right? As you proceed with the product design, you figure out that you are actually not hitting the perf, or you are breaching the power limits when you have come down to a stage where you are basically about to tape out the product into the fab. That's again a serious loss of time. And there's again a risk of missing customer commits. For example, one example of regression I can just say, like if you planned a CPU with, let's say, N cores, and you estimated the performance to be, let's say, something like P. Now, you will figure out probably sometimes it does happen that you will actually get better performance with fewer cores. Let's say less than N cores, you might get better performance. Well, technically it may happen, but it's actually bad optics with the customer who is paying for N cores, and you can actually get better performance with less than N cores. So these are the things that need to be really caught in the pathfinding phase and not really at the end of the product cycle. And while solving these challenges, there's also a silver lining. We actually end up having new business opportunities. And this is the beauty of this kind of the work we do. And the new business opportunity, a very trivial example is a product being refreshed. And this is a very simple, opportunity or a kind of product refresh with a fast turnaround time, but there are more. You can actually harness a lot of business opportunities while solving these challenges. That's the beauty of this kind of work, right? And yeah, so now I come to the hardcore science and technology of power estimation and performance estimation. This is a very simplistic block diagram that tells you what goes into P and P. Right? So there needs to be a performance simulator for which you need to know. Now we are going to find out alternatives for this power and in performance simulator and what the block given by power rollup later on. But to start with, let's assume that you have no other reference in your product map and you're starting from scratch. Then you need a performance simulator which will actually simulate the performance of the architecture that you're going to architect and eventually build it, right? And usually there is a strong dependence of power on the performance. And therefore, there will be some inputs from the performance that goes to the power rollup. And I say rollup because we are basically trying to do a divide and conquer approach in power. It's not so, I mean, we have so many different power rails running inside the system, and you have a lot of different functionalities, different types of power reduction methodologies have been employed at the circuit level, and sometimes even at the device level they are optimized. So it's basically divide and conquer approach. You find the power of smaller units and then bring it up at the circuit level. But this is a very simplistic view. This doesn't solve any of our problems. It at best tells what is the science behind this. Going further, right? Now, you'll just set some terminology right so that we all are on the same page and there's no confusion on. So performance P, let's call it P, it can be in terms of time or it can be a reciprocal of time. It's just how we take it or how we interpret it, right? If it's in the units of time, lesser the number P is faster the system. But if it's the other way, it's again the opposite case. But this is not how the industry works. Usually P is something like a score given a benchmark company comes up with a set of sub workloads, and it will say that a particular score can be a harmonic mean or a harmonic or a geometric mean of a certain scores of sub workloads, and the individual scores of the workloads may itself be different, right? Now, it's very physical to say that my 3D Mark 11 GPU gaming benchmark has FPS of 30 frames per second. That's very physical. We can easily understand it. But if I say that the iSpec 171T CPU benchmark is, the score is 1750, I really don't understand whether it's a high score or a small score or how is it. But that's how things are benchmarked against, but there's always a basis for that. We can actually get into it, and I can give some references to go and do some research on that. So typically when I talk about performance, let's keep it that it's basically coming in terms of time or the reciprocal of time, and basically telling us how fast is the workload being executed, right? How fast the work is being executed. And that's what we will actually be looking at. So the end scores, the end performance metrics can be different, but the basis is the same. So let's keep this hypothetical reference for the rest of this tutorial. And this is by no means the ideal ideal reference. It's purely hypothetical. So let's say I have some 4 cores designated by C1, C2, C3, C4 on a bus interface. It's typical CPU architecture, but it has a memory subsystem, and it has a ring or a network on chip that actually provides a way to communicate, for the core to communicate data to memory subsystem or the switching fabric for peripheral control interfaces and so on. Also, there is a cache. Now, on top of all this are the circuit level parameters, like what is the clock frequency, what is the voltage to be supplied, what's the electrical parameters, all these are there. But architecture wise, this is a very typical and a hypothetical example to keep in mind as we proceed in this tutorial, right? So I'm going to refer to this back and forth so that once the ideas are clear, it's easy to actually map it to another architecture or design at a later stage. Let's also keep G1 to be another GPU, an integrated GPU, and rest of them are mostly some kind of interfaces that allow for data transfer back and forth. So how fast the data gets transferred from one source to another destination and vice versa. this is what it all means in having defined as performance for a particular workload. So now we double down on the simplistic picture that we started, and this is because we want to identify what are the good candidates for us to actually use when it comes to pathfinding. What are the good candidates for what to build an ecosystem where we actually go and do kind of PNP in various other checkpoints in the overall product milestones, product development milestones that we discussed. Right? So we want to have it as an ecosystem or as a framework, right? So we want to bring all of them at one place ideally. It's not yet happened, but this is a kind of a wish list that all of them come together so that I am able to do this kind of analysis rapidly and in any at any point in the product development timeline. It is not just pathfinding. Pathfinding is very important, but even beyond that. So what I'm trying to do here is that actually apply divide this problem into two branches. One, I call it first principles, and other is it's mostly top-down methodology. But since we are more obsessed with kind of AML techniques, I use the same terminology here. So you can have a performance estimator eventually that will work either on first principles method and or on AML methods, and I'll come to that. And which one is suitable when is what we try to discuss in this talk. So a perf simulator, perf estimator will also have at the back end perf performance simulator. And you also have something which we are now bringing in and try to talk about the importance of it, that silicon performance measurements is what we're trying to bring. And in this context, I'm just trying to set one more point here. So what we'll do is we'll talk about whatever the product for which we are interested in the power and performance is like generation N. And for this and any past product as generation N-1 or N-2 and so on. Right? So what we want to do is to basically have a very compact model for performance estimation. Now, clearly, I can't go and architect an entire performance simulator in the pathfinding phase for a new architecture. It will take 6 to 8 months easily. Now, that's not a time for which we have to decide whether we want to have a product or not. So the performance simulator, there are various ways of implementing it, and that's why we are trying to tell this, all this as a set of components of this ecosystem. So we will have a performance simulator, which we will list out what are the candidates, and then we have what are the methods by which performance estimator will work on. Here we have broadly classified it into two first principles and AML methods, and next we also talk about what is the target configuration, what's the base configuration. These actually mean what are the basic parameters of an architecture. For example, it's very clear that clock frequency is a measure of performance in some sense. It's not the everything. It's not clock frequency doesn't tell everything about performance, but it is one of the parameters which will influence the performance, obviously in circuits like GPU or CPU and so on. Right? And we have just in the past slide we saw that there are so many other resources here in like number of cores, what type of interfaces that we have, and of course you also have cache and you have memory subsystem. These two are on the two different hierarchical planes in the system. So they come with their own parameters or configuration setup. So in that sense, the target configuration and the base configuration give you a way of specifying the architecture to the performance simulator. So going further, right, and we will now start with what we mean by first principles, and then we'll also list out all the possible performance estimation methods. And again, I'm just trying to recollect here and trying to bring everybody back on the same page. Now we are discussing the performance estimation methods. Soon we will go to the power and eventually connect the two. So here, RTL simulations are something that is very straightforward to understand. Once you have a design, you obviously can do a lot of things with RTL simulations or even netlist simulations when it comes to power. But on performance side, we restrict to RTL. And then you have emulation. It's a faster cousin of RTL. again, both RTL simulations and emulation would not solve the purpose of pathfinding for us, right? So the next best thing to do is to go and build a performance model, and it's mostly typically it's called cycle accurate. It's not always cycle accurate, but reasonably close to being cycle accurate. So cycle accurate performance model may be written in C, C++, System C. It's still huge development time compared to other solutions that we have on the table, but in any case, that's much better than having RTL simulations or emulation in terms of time. So you have an opportunity to execute much workloads much faster and understand their performance. You can do a lot of what-if analysis with respect to new features that are possible. And if you compare the same with respect to RTL simulation and emulation, we really fall short of expectations on two or three important factors, right? The time that it consumes, it's going to be huge. And again, RTL is not something that will be available for you. A verified RTL that is golden is not something that will be available at the pathfinding or very early stage in the design flow. So second, it's rather difficult to support benchmark workloads. We can support micros in RTL simulations, but imagine having to run the entire iSpec workload or a 3D Mark 11 gaming workload on RTL. I mean, even a C++ System C performance simulator takes 15 days to run one frame with best of the compute resources at your disposal. But RTL is something which is unthinkable. I mean, we would say it's rather impossible. So at this point of time, our concern is for the pathfinding phase, how fast we can get the performance numbers. And that's why there is some distinction that can be done in the last two methods that are available to us. Right? So what we are trying to look at this as a top-down methodology employing AI and ML techniques. It's mostly ML techniques. We learn models rather than create models. So that is the overall principle of using AI-based pre-silicon performance estimation. That's one of the technique that we'll discuss. So here the key point is learn models rather than create models. We'll start building a large database of training sets and eventually look at how performance varies for a particular configuration that I'm thinking about, and I can do a lot of what-if experiments when it comes to architecting the overall SoC. The second one is an extension of the first, and this is really based on the post-silicon data. So we'll look at something like this. Not all products are designed from scratch all the time. Take the example of CPUs, GPUs, and all the compute platforms that we have discussed about. It's always an incremental change that takes place between one architecture to another architecture. And this is very important in the context that we should be able to benefit a lot out of the silicon that we already have. But from the point of view of the observability, what the previous silicon gives us is rather limited when it comes to power and performance. We just get some numbers when we measure them, right? We just get some numbers to measure them, and we cannot probably go and do a backward analysis to say, okay, changing or introducing a certain feature or changing the spec of a particular microarchitecture will actually help us get a better performance. So that kind of analysis is something difficult to get. But in spite of it, there's actually some hope in terms of what we try to call as performance monitoring counters based ML assisted performance estimation. And we will come to that. And it is in this place and at RTL simulations that the verification technologies come to our aid as for power and performance engineers, how we use verification techniques to basically achieve our goals through these methods. So I'm going to turn off some of the blocks in this overall block diagram to say that this is the block diagram if I would take a first principles approach. First principles approach is rather a bottoms-up approach. So I wouldn't need the bottom 3 or 4 blocks that are like whited out here, and those which are highlighted in color is something that I would want to be using it. So this is where the different flavors of performance estimator, performance simulator come into picture when we try to build the overall ecosystem for rapid PNP estimations. The in spite of all this, it's just the basic same principle here. Now, it's a very very simplified picture of what a performance simulator does. Let's say we have some 6 units interacting in this fashion, okay, and they have their own latencies. Eventually, the performance is a function of um, trying to do like something like a relay. It's kind of 4 into 100 meters relay that one sportsman, one athlete passes a baton to another, and they pick it up, and then so if there are bottlenecks in any of the pathway, you're obviously the performance takes a hit. The timing to complete the workload or a race takes a hit. So in this sense, this is basically what we generally call as time graph. It shows the dependencies of a particular unit on the rest of the units and how they actually influence the performance. On the left-hand side, we have clock cycle numbers listed out. Now, assuming that S1, S2 are basically the latencies. So eventually, or something like a transaction that takes some X number of cycles everywhere, and in that case, the overall performance is actually sum of all the latencies in the critical path. So that is the overall principle of a performance simulator. It certainly is not as simple as this. Is highly simplified only to explain this essential idea that we are taking the max path of data flow from source to destination when a workload gets executed, and that is what reflects as performance. Right? So, so this is the basic idea used in a cycle accurate performance simulator. And again, as we said, even if you were to model this architecture in C++ or System C, it still takes a long time to develop in the first instance and also even run an actual workload. So there are options now to optimize. Like we engineers, we try to see what, kind of cut corners and see, instead of doing the most accurate engineering, what is the just good enough engineering that we can do to get some idea about it. And let me come back to the most accurate one at a later stage. So that's kind of, again, a divide and conquer the complexity approach here. So what we try to do is bundle several hundreds and thousands of clock cycles in one interval. Now, I0, I1, I2, and I3 are actually intervals. This is only an example once again, and I'm just going to tell that here, whatever parameters that are portrayed across each unit in a particular interval is basically the latency that it encounters for a particular workload. So here, instead of taking the, we are now making our performance simulation more gross than doing something at a cycle level. We are doing it at an interval level. And at this place, we are trying to look at what is the bandwidth across each interface of this unit and in each interval. Now, as the bandwidth increases, or it comes to closer to peak, we will make a hypothesis that is basically the bottlenecking unit, and we vote that unit to be a bottlenecking unit. And I have just randomly placed some bottlenecking units here and take their micro architected latencies as the guideline to go and build a time graph for this particular workload. And in this process, what happens is that we have the chain of bottlenecking units. We add up their latencies and come up with a performance number, or at least something that reflects the performance. Again, it's not as easy as we speak with this particular picture that is visible, but again, the principle is the same. As we get into the details of micro details of building a time graph, we will understand probably that the performance can actually be estimated with reasonable accuracy by bundling a lot of clock cycles into certain intervals. Now, the question is, I have the performance simulator for a particular product already. It's pretty mature. Now, what do I do? How do I do it for the next product when I go and modify certain features? I add the number of cores, I increase the cache sizes. What is going to happen here? So that is the whole idea. And in that context, you will see that we go and define new intervals where the bottlenecking units now change. So now in the time graph, the sum of all the time intervals I0 prime, I1 prime, I2 prime, and this gives the new performance for us. So this is a principle of a performance simulator that we said is based on first principles method. Now let's take a look at the tops-down approach, and this is where the boxes on the left side are whited out. They are not needed, or at least they're not helpful, but it is the other flow that we depend on, the silicon performance measurements, that matter here. Again, we have two levels of approaching this problem with this up, and this is what we are trying to use for left shifting our performance projections in the product development milestone. As we see here, right, and I'm just copying a piece of the product development milestone slide that I showed here, and try to relate what is it that we are going to do here with that. So it is in this phase that this becomes important, and here we are trying to understand what is the right configuration of this architecture that needs to be taken in for the overall product development phase, right? We'll take this as an architectural basis to go and do the RTL development, if necessary, borrow from the previous work, or we actually go and create new features, and eventually that's what we refer to it by design intercept. So we take all the learnings here. Now these three blue blocks are basically from power and performance point of view, but essentially the pre-silicon design phase runs parallel to this phase. Right? So that is why we are saying it as a design intercept. Right? We are going to intercept a design process with the learnings, and after the perf checkpoint here, this is actually past the pathfinding phase. Right? But even so, how can we do a performance simulation or estimation as fast as possible? That is the problem statement here. So if you look at this, this is a kind of flowchart representation of the previous picture. Traditionally, what has been done is that basically you have an architecture and a spec created, you take it to the design, and this is where the actual verification utility comes in. You will typically have a test suite which runs a lot of which excites the design and the test with a lot of workloads, mostly micro workloads, and then you determine the performance metrics like bandwidth or latencies from the RTL design that you have. So if this is satisfactory, you take it. If it's not satisfactory, you actually come back and you reconfigure the design and run back again. So not all of them need to be done by RTL simulations. Even understanding of the basic properties of a core, it can lead to this kind of iterative cycles. And that's what I wanted to highlight by saying a traditional methodology. What can be done here in terms of basically using AI and ML methods and try to speeden the activity of pre-silicon perf estimation. Right? So again, you create a lot of design parameter states, at least vectors for exploration. Eventually, you either constrain each of the spec parameter, or you basically generate all the possibilities that it can take, or to conquer the complexity, you basically randomize it. So these are basically verification principles that are getting into performance estimation. Right? So you do you trigger the circuits with test stimuli and do a performance analysis, put it as a training data. And there's a neural model. I mean, we can do a lot of discussion on what kind of model is good for this, but at this level, at a high level, I'll retain it as a kind of neural network that's actually going to learn a model saying that if my input parameters are X, Y, Z, my performance in terms of latency and bandwidth is going to be, let's say, A, B, C. So once this is done, you come up with an intermediate architectural spec that you want to basically go and model and estimate power before you go and start the design phase. we actually take this prediction path, and conceptually it's pretty similar to all other ML flows, regression flows, wherever we use it. Conceptually, we're just borrowing that. Right? But when it comes to implementation, there is a kind of ecosystem that is required, and here we are trying to use whatever is available at that point of time in the product development milestone. And in this phase, it's still not prudent to go ahead and do an exhaustive RTL simulation at the SOC level. So we still want to divide and conquer some of the approaches here. And this is where the AI methods help, right? And so just to bring this flowchart on top of this architecture, what we are trying to do is that each of them have their own architectural specs, and bus interfaces have a lot of FIFOs whose depths are variable and they can be designed. Cache sizes can be different. The ring and the NOC architecture can be different, and they have different latency paths with different latencies, and they all come as an input. So you will probably have an exhaustive database of all the microarchitectural components, but the bigger picture at SOC level is lacking. And that is when this particular flowchart kicks in. Right? This particular flowchart kicks in, and it's actually much faster than. Oops, sorry. Yeah, it's actually much better than traditional methodology, which actually relies more on your simulations or the regression environment to give you some idea about performance analysis. Having said this, we come to the most important part of this, actually. And we want to say that we want to put all those things back, and we still want to left shift our process to estimate power right at, estimate performance right at the pathfinding phase. Now, it is here that what is known as perform counters, it's called performance monitoring counters. Most CPUs, GPUs in the industry have it, but even if they don't have it, I'm going to pitch a case for having it. So it is here that in the long run up to development of advanced architectures, these counters were instrumented in hardware for debugging purposes. They were actually used for debugging purposes. So if there's a customer issue, once the laptop has been shipped and there's a problem with certain workload, we would actually take the trace from the customer and eventually go and debug this as to what's wrong with this. So it was based on a certain heuristic idea, and it was designed based on the experience with the customers. Right? In the long journey leading up to the current architectures of CPUs and GPUs, this was actually implemented. So these are basically hardware counters which actually count events, and they do that they can be programmed to do that in real time. You design certain drivers to, and actually once the product is in silicon, we will be able to extract this kind of counters, and these are spread far and wide in the architecture. Today, there are more than 450 or even 500, 600 counters that are available, but not all of them are useful. Once again, these were instrumented to basically debug customers' problems in the past. But the idea is this: if I am able to switch off a particular feature in an architecture, extract the counters, and if I enable a particular feature which is actually enabling performance, let's say multi-threading or something, using multiple cores at a time, and so on, then I get two sets of counters which were actually counted and registered in the silicon, in the hardware. And I now compare, and I also get the performance numbers out. So the hypothesis is that I should be able to model the feature, model the impact of the feature on the performance as a function of difference between the counters. And by difference, I don't necessarily mean the numerical difference between the counters, but the behavior or a pattern in the way that they are varying between when the feature is switched on and when it is switched off. So this is an interesting aspect here, because you can run the workload of your choice with the OS enabled. So typically, if iSpec is a golden benchmark that most companies use these days to benchmark one CPU against another. You already are already able to run the most recent benchmark on the silicon with the type choice of OS that you want to run, and eventually get out these performance counters. So if this is the case, now obviously it is just not one feature or one specification that is actually determining the performance, a whole lot of them. And as I showed here, cache size can influence performance. Whether you use 1 core or 4 cores, it can influence performance. What is the latency of the NOC or the ring, that can influence performance. So having said all this, you now have a kind of a homogeneous data that is dumped out. It's not so trivial to actually go and decipher the reasons for performance deltas manually. So it is here that we expect a ML technique to learn the model rather than actually create a model. So it's actually a tops down. So the hypothesis is performance can be modeled by a subset of performance counters. We start with this hypothesis, but we need to identify canonical counters for performance. Not all 500 are useful. Maybe only 50 are useful, which will actually go and determine the performance, right? And you should see that the performance readout, the counter readout, has negligible impact on itself. So you don't want a observation mechanism to go and influence the performance on its own, right? So very quickly, what are the kinds of counters we need to look at or address? It's pretty straightforward. Now, any typical performance model will look like a roof. It's called as a roofline model in theoretical computer science. So it's not going to be as sharp as this curve. There is actually two regions here. One is a compute bound region, one is a memory bound region. It's a standard topic in any computer architecture textbook. We can actually go over that. But I'm just trying to tell that depending on the region bound that you are trying to analyze, you have a set of counters coming at the interfaces that I pointed out here. So all these P's are basically lying somewhere. They're trying to indicate something like a counter in the L3, L1, or L2, or something like that. So it's I'll not go into the details of this architectural representation in terms of performance counters, but it suffices to say that each region in the performance curve can be mapped to certain counters in this kind of in this dashboard. Right? So this is something a purely post-silicon exercise. And for the next architecture, let's say I have a golden post-silicon data that's now, I now can go and look at what are the features to tune to actually get the performance for the next architecture that I'm going to come up with. Obviously, if it's a brand new one, you already have to go from the first principles approach. There's no way here. So here is where ML technique is getting used. Again, I don't want to get into the details of this. It's just more details, but conceptually it's just the same. Pick the raw performance monitoring data. So you get it through the time graph, and finally you create a data set to learn what the performance is for different features being turned on and turned off. Again, get a canonical set of features, maybe using something like a principal component analysis, typically used in signal processing applications. And then you train a multi-layer perceptron performance prediction model to get the performance of another architecture. Having said that, I quickly move on to power. And even in the power estimation ecosystem, we have the same two kinds of techniques. Obviously, the purpose, the algorithms are different, but you still can have a first principles approach. And what I'm trying to say is that there can also be a ML-based approach. So here, instead of measuring performance, we will be focused on measuring power. And this is where, although this flowchart looks complex, but the algorithms themselves are simple. The simple reason being, the total power of the SoC or a system is actually sum of the powers, right? But that's not the case in performance simulation, and that's why you require an elaborate performance simulator. But in power estimator, you do not require an elaborate power simulator, just like what we have on the performance side. So I'll leave this at this flowchart level. The details are very straightforward in the sense that you know what inputs actually go into power, and here technology is a very important component. Which process node are we going to use? That will also determine the switching capacitance, and it will also determine what is the leakage and so on. So again, early power projections is exactly the performance counterpart in the pathfinding stage. So dependence on a detailed performance simulator is not a good option, because we would not have designed one in any case. Or performance models for power simulators mature very late in the design cycle, and they actually at best serve as kind of documentation purpose later in the game. So workload scalability also is not a simple fact when you try to actually go doing first principles approach for power estimation. So this is because there's a large number of power states, right? I mean, any single, let's take a CPU with 256 instructions. At any given point of time, it must be in one of those states. And if that's true for one core, you have so many cores and you have so many other infrastructure in the CPU. So obviously the number of states for which you need to characterize the energy in a first principle approach goes for a toss. So let me again go and look at what we can do from ML technique point of view. We have a training path and a prediction path. In the training path, we have simulation, silicon measurements for power and performance, because the residencies in which a particular unit resides in an active state or idle state is actually given by the performance simulator. So what we could do is to basically pass through this training path, taking the power measurements and eventually train by, here I have mentioned it as a quadratic programming technique, but obviously there can be multitude of ML techniques that can be applied here, and it can go to a very complex neural network as well. Right. So once we get the new scaling, new energy cost for the newer architecture that we are trying to target, or the target config that I mentioned here in the prediction path, we eventually be able to get the new power and coupling with the performance that you get in the previous approach on performance that I spoke about. So that's where you actually start getting a linking performance at power. Right? So these are some of the aspects of algorithmic aspects of how we try to get the train the power model. So this is the one that we measure for a overall core, and these are the constituent ones. We don't necessarily try to predict all the clusters, and it's not required. If we have 3,000 power states and only 300 contribute to 90% of the power, there is no real return on investment in actually trying to come up with simulations for RTL simulations for another 2,700 states, right? So that's how we try to optimize and eventually get a cluster level breakdown. And this is the these are the mathematical aspects of linear regression that I'm talking about. And if you refer to the convex optimization function in Python, the NumPy library, you will actually start getting a handle on this technique in trying to do learn the model for power based on silicon measurements. Right, again, these are just, I want to skip a few in the interest of time. So I'm just trying to tell that once you get this, you have technology scaling factors coming from the fab, applied on top of them. You already have some estimated gate counts that will help you in arriving at the power for the new product. Yeah, this is what I was trying to suggest here. So depending on how the configuration looks like for your new architecture or new product, we determine the scaling factors based on some first principles and eventually get to the power estimate. The overall ecosystem is again something that is important here, right? Because we don't want to do in a piecemeal fashion where you do something and you throw it at the end of that product development cycle is over. Because there's an intricate dependence between the kind of products that we are coming up with, the circuits and the architectures that we are coming up with, and it doesn't make a sense to actually discard the techniques that you already used or data that you already collected. And that is the reason why you actually go through all the other bottoms up principles also when the time is available, and you will actually use that to fine tune or correct the power projections or estimates in the long run, in the timeline for the flow. Getting this back, so whatever we discussed was like the bottoms-up approach is very helpful in the power and perf checkpoints on the right side of the screen. But when it comes to pathfinding and doing what-if analysis and something that needs to be done rapidly, there's a strong case for actually using ML techniques to come up with this estimates, right? Power and performance numbers. So this is trying to put things back in context to the same product development timeline that I actually started with. The most important point is eventually we all rely on, we are saying that there's actually a golden reference to come up with a new power number or a power number or performance number for a new product. Now, how does this golden reference come at the end of the day? This is the post-silicon validation, and this is where the validation environment kicks in for power and performance. You can see that the activities of power and performance itself is very small. But in order to trust the numbers that you get, to treat it as a golden reference for future architectures, it has to pass through all these phases. So I have kind of simplified the overall chart, and it's not this simple, but I just want to highlight that this post-silicon validation environment is very critical for us and in actually trying to come up with new numbers and come up with not on a standalone or an ad hoc basis, but to actually integrate it with an ecosystem in future, right? And this is the overall idea, or at least the pitch. Well, so final thoughts. So I kind of raised up on power, assuming that it was quite similar to the performance estimation flows. Yeah, feel free to ask questions in any case, but I just want to come up with some final thoughts here. There is no conclusion right here, but final thoughts, right? So you have two branches for PNP estimation. One, first principles, bottoms up, and we were able to come up with a pedagogy of something like this. Right? Now, is it possible to mix each other for performance power? Yes, it is possible, depending on where we stand in terms of maturity of the components that we already developed for past products. The reasons, the pros and cons are the same, but what we are trying to tell is A and ML based principles top-down methodology is based on a golden reference. Now, how we actually transform that golden reference to what we want is our smartness. But in the other case, we always land in some shortfall in the accuracy in the bottoms-up approach. We also have to take a hit on cost. We also have to take a hit on resources and the time consumed in coming up with estimates. So with this, I just want to leave two questions open here. Now, what if we don't have performance monitoring counters? So that's a very important question to ask. So suppose my advanced process node enables us to actually go and fabricate huge system on chips, let's say a very big FPGA. Now, if it has 10,000 RAMs at my disposal to use when I map an application, can I actually have 10,000 counters only for that? We are trying to make the performance monitoring counters architecture more and more complex here. So where's the right balance? That's the question that we have to ask ourselves. We are trying to come up with a common framework for all compute solution. We are going to hit this when it comes to large. So you have a very large GPU with a lot of streaming processors. So more than 512 for a high compute high performance compute solution. So how many counters can you actually have them, right? So that will make the performance monitoring counters architecture more and more complex. And how do we handle them? Right? That is one important point. The last question is what is more like a final thought and a kind of conclusion as well. Sorry. So I'm trying to tell that. So post-silicon validation is critical not only for today's product, but it is critical for tomorrow's product also. Because this sets the golden reference for us in terms of generating power and performance estimates for the next architecture very rapidly. So to get that right, to get my next architecture into the market right, I need to have done a very good job at the post-silicon validation of the previous product, right? So it will now trigger a chain of excellencies in the whole roadmap that we need to have our verification and validation environments in great shape to go and do rapid power and performance estimation. So with that, I try to conclude this, but feel free to ask questions. There are some of the references that one can quickly pass over to understand the basics of this trade and art. So yeah, that's how to say, especially on the benchmarks, and some interesting notes available on the net that one can easily capture. Right. Questions? Yeah, we can take questions. We can take questions. So we can take any questions here. Something was not clear at the fag end, feel free to. All right. So thank you very much. Thank you for providing me an opportunity to share these thoughts with you. And I conclude my tutorial talk here. Thank you. Yeah, sure. Yeah.
So this means we are doing a system C simulations. I think it's maybe the better thing to start with than performance simulation.
Correct. That's right.
And again, if in the system C simulation means on that model means one on your take how easily we can do the power estimation and all.
So yeah, actually, system C modulation itself doesn't give you power. Yeah. The point is that we have to instrument your model in such a way that it dumps out some of the critical stats. Stats means, let's put it statistics or you just like we have hardware counters in the silicon, you can actually have counters in your model. Okay, and when you run the simulation for a particular workload or a micro, you will obviously have a count of all that activity that's been there. So power is basically a function of activity, voltage, and frequency. So let's keep voltage and frequency apart. So it's basically you're switching capacitance, which is actually a function of activity. Now that activity is something that you can draw from a system simulator, a system C power performance simulator.
Okay, we'll take a traces from the performance counter.
Correct.
And again, from there we can analyze the power
on silicon, it's performance counter, but the same thing can be instrumented in your model also.
In the model also. Correct. Means, so the performance counter traces can be used to estimate power also.
It is required.
It is required. It's a dynamic power.
Yes, it is required. Okay. In some way, you need to understand what is the activity for a particular logic to estimate power, right? And this is one of the means.
One of the means.
Yeah. If that's, I mean, that's why I was trying to tell that there's a possibility to mix and match, right? There's a possibility to stop function. Okay, it's possible to mix and match a purely top-down approach to a bottoms-up approach component as well.
Thank you. Thank you, sir.
Okay, thanks a lot.
I want to express my heartfelt thanks to Mr. Vivek for your insightful presentation on power and performance verification. Your expertise provided a valuable perspective on optimizing efficiency and ensuring the robust functionality in our systems. Your contributions has deepened our understanding of the concepts. We are grateful for the knowledge shared. I would invite Mr. Hari Prasad to hand over the token of appreciation to Mr. Vivek. Thank you. Moving on to the next talk. The next speaker is Mr. Pradeep Babu, who's a director of engineering group at Qualcomm. Pradeep Babu has 24 years of experience in SoC design and verification validation. He's an expert in automotive functional safety verification and has led multiple ASL DB SOCs in Qualcomm. He has established the safety verification flow and process across Qualcomm IPs and SOCs development. He's engaged in automotive customer audits of ISO 26262 compliance process, audits and certification. He's experienced in SOC power and system verification. He has delivered successful products across multiple application space in the industry, such as NFC, UWB, automotive infotainment, ADAS, and high-end security DVR markets. Pradeep Babu received his bachelor's degree from Madras University. He has published 2 US patents and he has published multiple papers. He's actively contributing to the verification community. He's a part of multiple conferences conducted by Cadence, and he was one of the panelists on the DVCon 2022. I'd like to welcome Mr. Pradeep Babu onto the dais and for the technical talk on low power verification. Thank you.
Which one is the marker? Pointer. This is a pointer, huh? This is a pointer. Up and down. Okay. Folks, so today I'm trying to cover the low power verification state of the art, and so I'll be more focusing on high level power verification strategy and how it is evolved over time. Let's get into this one. So Qualcomm, I'm more trying to cover around the Qualcomm plus the industry, how it is evolved. So if you look at it, the power architecture primarily has been evolved in Qualcomm side. It's more of the mobile architecture. So it's centered around low power mobile applications. So that's where it started. So over time, if you look at it, the mobile phone has, these are the major areas where we are kind of investing. So it's like edge AI, camera, graphics, and there are multiple processing elements. And how about the connectivity network like 4G, 5G kind of solutions, right? So these are the areas where the power has been more centric around how do we optimize power and get the product with the right power targets. And if you look at it, like it's more focused on these are the key metrics we look at it, like on-device intelligence, how do we support on edge AI and graphics processing, and performance and low power are the key targets. So we have to be careful about how we are evolving the performance as well as how we trade off for the power requirements. So the low power is a very key factor and it's a differentiated selling point for many of the companies in the industry. And it's always not about the performance, the power is also an equally critical factor. And so if you look at it, the low power, the focus was started with the mobile kind of applications and now it's expanded to the multiple market segments. And each market segments, the power requirements are completely different. I'll be covering it some of the high level points when we go to the subsequent slides. But if you look at it, the complexity wise, starting from the wireless earbud and smartwatches and AR, VR applications and laptops and automotive, right? So these are different market segments where finally the chips are going to get used and the power requirements are completely different on each of these areas. So that is where how do we scale the low power concepts and the corresponding verifications which can scale to the different market. So yeah, so scalability, right? So the power segment wise, if you look at it, the SOCs are centered around these areas, right? Deep learning algorithms, we need to have cloud integrations, camera processing, and heavy computing applications and sensor processing. Some analog components will be there, right? So all these are the key factors we look at when we build a SoC, which is scalable for different market segments. And if you look at it, the smallest of the Bluetooth SoCs which we make, it has kind of MCU, some of the security requirements and Bluetooth interfaces. Then it's kind of the next level, slightly expanded complexity, the connectivity SoCs where we have more functions, Wi-Fi components will be added. And comes to the cellular SoCs, the modem comes into play. So the 4G, 5G modems, what we are integrating, it's expanded view of the architecture, and then we have securities. And application SoCs where we go more running mobile applications, compute applications on top of it. So you need to have more higher like a DSP engines, CPUs, graphics engines, and display, Wi-Fi platforms, camera, security, right? So more and more, if you look at it, the SoCs catering to different market is keep expanding with the different new features. And the last one, the high end, what I kept it is the AI, ML processing on chip, edge AI becoming a new topic where we are investing a lot. So AI engines is taking the significant space in the device, other components which is involved, right? So this is the way it's kind of scales, and the power requirements for each of the segments are completely different. How do we meet the demand of all these areas? Okay, so just want to touch upon like the biggest versus the smallest, like what are the power demands from the application point of view. So when we look at the compute kind of application, what we go for the laptops and everything, so it's going to be a heavy footprint silicon. It's a larger in size, and the power and performance benchmark is very key. And each of the core which is sitting inside either a GPU or processing units need to be targeted for specific performance targets. And it also comes with the cost of power. Like power, you cannot be having a uniform across. You need to have a hotspots where high performance nodes are running. And how do we manage the power for it, right? So compute comes with a different demand of power architecture and verification. And when it comes to IoT, it is not about the big size, it's about the small chips, but it also has a requirement of battery life, right? So the days of use and the critical KPI for the IoT, we need to see how much load we consume and what is the battery life we can offer for it. And when it comes to the automotive, is another segment where the safety is a key major role. So how do we relate safety and power? So in automotive cases, how fast your device is coming up, and you are able to open up your safety eyes around your car is more important. So how fast we boot it, and your power on sequences, and the device application state coming in certain time is very critical for safety applications, right? So this demands for a different power use case scenarios. And when it comes to the like AR, VR kind of applications, so it's more of a multimedia centric, and the camera displays and GFX are playing a critical role. So here it's more of the thermal limits and the power dissipation factor, because it comes in a small form where you put it on your eyes, and you cannot have smallest amount of heating there. And the thermal factor is very key, and we need to have architecture and verification center on those areas. And if you look at it, the last two different market segments, like cloud server is another, baseband cloud server is another area where you will have stack of chips going in a rack, and how do you manage the power dissipations and power architecture, how does it scaling for that. And that's on the cloud side. And mobile side also, it's a handheld devices, so the stringent power requirement, the device, the power cannot be at a center on certain area, and it has to be spread across uniformly, and the heat sink and all those factors come into picture. And shrinking tech node, and we have more challenges on the power in terms of the leakage components. And the tech nodes goes smaller and smaller, the leakage becomes a more difficult factor to handle. So again, what are the different architecture, and how do we manage the power aspects here? So if you look at it, now power is not just a one simplistic architecture and you have a verification design around it. It's about the market segment what we are targeting. And every segment you cannot have a completely different architecture. You need to have a scalable solution of power where you can have some common our scalability and the infrastructure built around to all the markets. So this is where we invested time to make sure that the verification and architecture for the power is scalable across, and all the device which we make across market segments are able to utilize the common framework. Okay, so now let's go into slightly into the low power modes. So I'm just setting the stage for widely adopted design concepts. So if you look at it, most of the applications where power is always managed by a slightly different IC which sits outside your application chips, where you call it as power management IC. So most of the systems, if you look at it, you will have a supply, either battery or power supply, and there will be a power management IC which manages the power requirement for your application SOCs. And the job of the power management IC, it kind of manages the voltage regulators. It regulates the voltage based on your application need. And LDOs and switches are kind of part of the PMIC. So LDOs basically it kind of gives you the power on a specific node, and corresponding power rails will be given to the SOC. And there are common system clocks, analog muxes, and if you have application where the chargers have to be connected from your device, so the charging kind of interfaces will come from the power management IC. So this IC is full responsible for the power supplies going to your application SOCs. So when it comes to the application SOC, yeah, I just picked up one of the previous slide, the architecture one. So if you look at it, the SOC will have its own application partition in multiple blocks, and each of the blocks can have its own power rails and power management systems. And on power up, the requirement, the power supply will be default coming from the PMIC. And there are cases where if you want to optimize for different performance needs, there will be a feedback circuit where the application running in your SOC can go and talk to your power management IC to control the powers. Like for example, you don't have a particular workload to run on certain time interval. You can say you can turn off one of my DSP, which is not required at this point of time. So the application can go and tell the PMIC, okay, you cut the supply for this, or you run it at low speed, or my application does not need this high performance at this point of time. I want to run at low performance. Can you reduce my power, or can reduce the frequency of operation? So those kind of decisions are taken, and there will be a feedback loop. Always go to the power management IC to control that. And the power also is not a common power supply goes everywhere. So it kind of partition across, like digital logic requires a different power voltage level, like 0.9 or less than 1 volt will run. Memories requires a different rails, because mostly we right of go for the retention kind of modes where quick boot up. So memory will be always decoupled with the logic rails. And IOs requires a higher voltage because it kind of routes a longer signaling on the board, so it cannot operate on the core voltage range. So these are the different voltage requirement. DDR requires a different, and if you have analog components or RF, which also requires a different level of voltage level, it cannot share the other rails. So if you look at it, these are high level classification. So each of these components in the device requires a different power rails and different controls to manage those independently. And so some of the example methods, how do we manage the power optimization? So the basic one is the static voltage scaling. So depends on your application state. You can decide you want to run at what frequency. If you are going down on your frequency, there is an opportunity to reduce the voltage coming into the device. So you always go back and tell the PMIC to reduce the voltage, because I'm going to operate at a lower frequency, right? So that is one possibility. And if you look at it, when you fabricate these devices, there will be different process corners devices will be available. So you generally call it as a slow operating process corner, or normal, or the fast corners. So these are different process corners will be available. So based on that also you can decide and what frequency and what voltage level you can operate your devices. So these are the simple techniques where we use some software control and there's some hardware feature control to control based on your application needs that you run at what frequency and at what voltage. So these are the combination, is kind of a loop circuit which will be continuously running with some monitors. And so the second methods which generally adapted across, it's a dynamic clock frequency and voltage scaling. So if you look at this example, so if you don't have DCVS concepts, so in your time of application, you expect once application come to a execution state, it's going to continuously take a power of the sustained, for example, 100% of your targeted power. This is not very efficient because you'll be burning a power a lot. So how do we manage the power optimization based on your application at a particular time interval? So that's where the DCVS came into play. So whenever you have, for example, whenever you have a application running, so you can give a maximum power to the full requirement to run the application. And wherever you have a not requirement to run at full performance, you can turn off certain things. So dynamically you can manage your clock frequency and voltage scaling to bring down your power consumption, and you can keep on switching based on your need. So when you do this kind of concept, so overall your average power is going to come down significantly compared to what steady state power consumption is. So this is another common practice being used to optimize the power. So this demands a lot of architecture requirement here, like each of these blocks supposed to work at different corners options, and then you will have multiple option to reduce your frequency and operate at different voltage level. This particular block can work at 4 different voltage points. The timing will be closed accordingly and different frequency corners. So based on your application need, you can always choose this IP. This IP runs at what frequency and what operating voltage level, right? So okay, moving on to the power mode. So where the verification challenge comes, still I'm setting the context here. So we talked about individual block can operate at different operating points. So I just picked some example like DSP, CPU, graphics, display, video, camera, right, and the full chip. And if you look at it, we talked about the PMIC can give independent power rails for each of these components. For example, for discussion's sake, we can take the supply VDD, LV, level 1, level 2, level 3. So these are independent power rails is given to each of those block or the subsystem. And the multiplication factor is the DCVS corner. So based on your process, we can say we will have 5 different variation of your devices, like fast. It can run at fast operating mode. It can run at fast 1, fast 2, nominal, slow, and slow 2. So these are the, let's say, process variation we can bring in. And we need to have hardware circuit to manage the process node. And then for each of these block, we can always have minimum of rail off state, like the block is off during an application, and you don't want to lose it content, then you go for a memory retention. You hold the memory content, but your digital logic can be off. So that's another possibility. And you can also have a logic retention. Sometimes if you want to go to low power state and your configuration of the IP, you don't want to reconfigure every time. You want to boot up faster. So there is a logic retention option also will be supported. So if you take any block, it can have all these variations supported. So that's where the challenge comes for us. So one block we have to verify at different process corner frequency and voltage being supported. And there are different power states supported possible, like a complete off or a memory retention or logic retention state. And each block will have its own kind of flavor supported, and then the combinations of those. So if you look at it, one block may be supporting fast 1, nominal, and slow. It does not have the scalability for fast 2 and slow. So this will be not applicable for this block for the application. Application will know this block cannot go to the fast 2 or slow 2. At the same time, the another block DSP second instances can go to the fast to and slow to corner, right? So there will be combinations of this kind of table, power state table will be created, and this will also become a product variant which we create, right? So this is the state table mapping for your power requirements. And another problem statement will have is the power state transition. So how do we transition from one state to another? So when you say I am already operating in the nominal and I decided to switch to fast one, what are the transitions possible, right? That also have to be validated. So simplistic view is that always these blocks can stay in logic on state, logic off and memory off state. And logic can be off, memory can be retention, logic retention as well as memory retention, right? So these are the states it keeps circulating. So and there will be multiple arc possibility for each of those. So these are the high level problem statement. One is the power state table for your entire chip. Other one is power transition. What are the transitions possibility and how do we verify those? Okay, so coming to power R verification scope. First step, we always do the functional verification. We make sure that functionally your blocks are good and we are integrating the block, and the next come to the power verification. Power verification is slightly always skewed from the functional verification state. And so when do we start the power? So when do we start the power verification is that once we build the UPF where each of the components, the power rules have been defined, then we pick up the UPF and we start the functional verification along with power. So the focus areas where we invest time is we talked about the isolated power domains, and there will be voltage domains where you have a voltage isolation required and you are independently scaling the voltage, and power island modes where part of your SOC will be completely island from the rest of the SOC. So you will have your own separate power rails coming from the PMIC. So that is the island mode of the behavior. And the power distribution network, like we talked about the LDOs coming from PMIC, there are power distribution network within the SOC also you will have. So power switches, supply nets and everything, these are the other areas where verification challenges will be there. And we looked about the state transition diagram. So power state of each of the block, how do we verify? And when there is a signal crossing between different power domains and different voltage domains, we'll have the level shifters. Isolation state when one block is off and another block is on. How do we isolate the block which is on from the off state? Because if you don't isolate, there will be a leakage going on the reverse side. And state retention, like application state, when you go to the low power mode, sometimes you want to retain the configuration of the IP. You don't want to configure every time. So state retention, how do we manage? And the switching activity for the power estimate. So these are the focus areas where power verification will be centered around. And if you look at the power stages in a development cycle, what happens is we do the verification when there is a RTL development phase along with the power information on the UPF. And this is one area where we do the first level of verification. Once you go to the synthesis phase where you will have the netlist and the UPF, there will be second level of verification. And once you do the place and route, the post tech node dependent netlist, so you do the another level of verification, right? So there are three stages in every development cycle. We do the verification, RTL level, netlist level, and the power place and route level. So these are the three phases. And verification side, if you look at it, power R verification. So primarily we are relying on simulation and some section informal. So as of today, the distribution, if you look at it, 80% we still rely on the simulation based, and there will be some 20% we go into the formal based verification. But sign off heavily dependent on simulation based as of today. The main cause where we are still sticking to simulation is kind of the 4-state realization. Whenever the power is off, you are able to correct the logic with X and Z. So the 4-state realization is very important for power verification. So we are still using the simulation because of the 4-state. Formal 2-state and 4-state is kind of evolving, and there are areas where we use the formal 4-state, but it has some more way to go. And similarly on the emulation side, so we can do the power verification with corruption based on zeros and ones. We don't realize the X and Z's as of today. So we can use emulation to stress out the power scenarios, application scenarios, but it is not going to be the sign off for us, because the sign off still we need a 4-state. So there are investment in the industry where we can realize the 4-state emulation, but it is also evolving. It is not in a state where I can shift all the verification to emulation with 4-state and sign up. It is not at that maturity right now. So these are the different power verification assert we use as of today. Simulation we use for the sign off. Formal really helps on the signaling level, connectivity, isolations and all, we use formal. Emulation is for the power use case level verification, we try to close, right? So these are the different power verification methods we use at different phase. Okay, so coming down to power verification at different phasing, what we saw the execution cycle, this is the phasing. How do we do? So if you look at it, complexity and versus execution cycle. So architecture and design phase, we kind of do the power models, and we do the low power basic sequence, the peon sequence validation with modeling techniques. And we also create SV libraries for different power states. And this does not require a RTL as such. We can define different power states and we can create a SVA library. And we also create a template test case based on the segments where we are targeting. Like for example, we talked about automotive chips need a faster power up sequence. So there will be a template which will always check that when off state to on state you transition for application, is it meeting a certain boot up time window. So those kind of templates will be derived at starting point. And power estimate also we will do without having the design based on the power models. Each power model will associate with certain numbers of power and different transition possibility we will estimate the power. So this is the first phase where we invest on the power, and there will be a validation around that. And when it goes to the RTL level verifications, our focus is mainly on the power on sequence from off state. How do you get your every block to be powered up, and there will be multiple sequences. As we saw, there are multiple power rails coming from your PMIC switch. What order these power has to be brought up, and it does not burn out your device, or it is helping you to meet your KPI requirements. So power on sequence will be an important verification we have to spend in RTL. And the power mode tables, what we saw in the previous slide, that is also one of the verification. We have to ensure that the power mode table is completely verified on all state possible. And power mode transition, each table entry what we saw from a different table entry, how do we transition? So that is the important aspect which we will cover in power mode transition. And when it comes to the low power state retention, we talked about memory and logic retention, right? So how do we take it to the retention state and come back to the full active state? That verification is focused in RTL level. And formal, we more focusing on the power state isolations as of today. So the signal which is running between off and on state or transition state, how do the signals are getting clamped or isolated? We more center around formal as of today. And power switch coverage and power control coverage. So we also invest time on coverage metrics here. Because the larger the chip, you have a lot of internal LDOs which controls the power at smaller segment. And based on the power dissipation, so on the backend side, you will duplicate the power switch so that you contain a smaller logic which is controlled with a local power supply, right? So there will be a lot of power switches in your design. So how do you make sure every power switch which has been defined has been covered part of your verification? So there will be a power state switch coverages and the power control coverages. For all these switches, there will be control generated from different segment in your SoC. All the controls have been covered around. It's similar to what we do on the code coverage analysis. There will be a power switch and power control coverage analysis we do. And also we focus on power use case verification. So this is where we kind of rely on emulation. Some of the power use cases we cannot do it at RTL level. We have to go for emulation. And we also invest time on power measurements. There will be a power targets for each of the application modes. So you create a sample use case, we run it on simulation. You collect the power activity data and then you correlate the power numbers estimate. So it's the first level, and we will do it one more time at a later phase. But first level we'll get an idea like what is being estimated on the previous stage and what we see with the real activity. We are able to correlate it or not. But this is not the final one. So final one will the subsequent stage. So this is all the activities happens in the RTL phase for us. So when it comes to the netlist level verification, so there are more closer to the real silicon kind of concept comes in the netlist, where we look at it beyond sequence, and again the power mode table, power mode transition we need to cover. Here the only difference is that all the rules has been defined in the UPF will be actually getting translated into the netlist. So you will really see your power net, ground, power net and ground nets are really connected to your cells, and you no more relying on the UPF definition which corrupts your logic. So now you have the real circuit in your netlist itself. So we have to do verification at that level because UPF might have some issues which will be exposed at this level. And if you look at it, generally the DFT phase, there is a test features will be added in the netlist phase. Many of the test logic will not be applicable, will not be available in RTL. So post DFT insertion in your design database, how the power has been impacted. So that verification we have to do. Power measurement at this stage is very crucial because this is still a kind of high level activity power. Here is where you will have the every tech node library cell which has been characterized for the power, and you will be able to really calculate activity power based on the real numbers of that cell. So this will be correlated very close to the silicon. So again we do the power measurement here at this level so that we can expect a closer number to the real silicon. So if you go to the post silicon phase, so again on the silicon we do the beyond sequence verification, power mode table transition, and power measurements we do in the silicon and try to correlate. If we find there are gaps on the post silicon, what we measure, then we come back and improve our process to make sure if there are any holes, we'll try to fix it. So overall execution cycle, every SOC we develop. So we go through all these phases, like starting from the modeling side during the architecture design phase all the way to the post silicon. And this learning will be taken on device after device. So over the time and multiple generations we have done, these processes are more matured right now. So we'll be very accurately estimating the power KPI targets on the pre-silicon, and we correlate to the post-silicon. And okay, so the last part which I just had one slide to talk about the thermal. So thermal management is verification is also another topic where if you look at it, this kind of some sample I have taken. So if your mobile phone or your device, when you take it, so when you do the power analysis later, so you will find some of the hotspots. So this is one of the challenge which power have to be managed. Power cannot be centered around or concentrated on certain area where it will kind of burn your device. So how do we manage that, right? So this is at the die level, and you can have at the full phone, you can see the power dissipation, how it happens. And in case of automotive and all, and even in the phone, the LCD touch panel, how the power has been utilized, right? So these are the sensitive power areas where we need to make sure the power is distributed or power has been brought down so that it does not damage your device or equipment. And so if you look at it, there are sensors we add in your device. So mainly we have kind of current sensors, so which looks for the high current consumption at certain point of time, and then how do we prevent damaging the device out of that. And there will be temperature sensors when you are really going to the high speed mode and you're running your application. So in isolation state, it may look over, but cumulatively when you run the application over a period of time, there will be cumulative effect of power is being continuously increasing. So there will be sensors which monitors your power state when you're running a high activity application, and it kind of tells the controller that you are crossing the limit, and the DCVS concepts kicks in, and which goes and tells application it's kind of heating up, and you either reduce the load of your application, or you switch to a different mode where you want to run, or transfer your load of your application to a different thread. So all those decisions software will take to make sure that the power is not heating up like this, and we have to manage that. And similarly, the voltage sensors also. So there will be voltage sensor which look at the sudden increase in voltage, and then it will give a feedback to the PMIC chip which we talked about to either manage the rail, or if the rail is going out of control, you collapse the rail. So these are some of the other power aspects which comes in your device, where you have sensors spread across, and you monitor those continuously while you're running application. And how do you control the damage out of this, and the verification corresponding to each of these areas. Okay. And yeah, so coming to the challenges more we are working on. So whatever we discussed so far, it's kind of addressed, and these are some new areas is thought for investments, and like heterogeneous and homogeneous chiplet is becoming more and more need of the hour. So because we are hitting a MFU limit for a single die application, so there are chips which are homogeneous and heterogeneous, and how do you manage the power at chiplet level, and how do you verify those? So these are one of the challenge area we are working on. And when it comes to the use case power estimation, so it is impossible to look at all the use cases and create a power profiling at one point of time. So how do we manage the use case power estimate? Because sometimes when you give the end device to the customer, you might have estimated for certain power targets, but customer may have a different varied use case. They come back and say that, okay, certain areas the power is not meeting the spec. So you need to have a knob in your device to manage those kind of situations. How do you create multiple use case and pre-verify, and then you qualify in your silicon when unforeseen use cases come from customers field, and how do you manage it, right? So that's another area where we are investing a lot right now. And emulation, we are working with the EDA vendors to realize the 4-state power verification, so that we can offload some of this long running simulation activities into the emulation. That's another area. And formal adaptation, currently we are using only for the interface power signaling crossing the boundaries, how do we verify all those things. But we also really want to use the formal on the power state transition adaptation. How do we verify without relying on simulation? Because higher the device size, these are going in like weeks of simulation time. It's a time consuming work. Formal can help us on this area. These are the areas we are investing as of today. Yeah, so then if you look at it, yeah, I think, so these are the slides I put together high level to capture what are the power challenges we had, and what are the verification areas we are working on, and what are the future challenges. Yeah, if you guys have any questions, we can talk about it. You need a mic.
A couple of questions.
Yeah.
Okay. In the first slide, you put some 7 power rails typically, right?
Yeah.
So for the application SoC, so that's the typical number you have for application SoCs? No, even before. This is, I think, 10 because of these ones, right? Those are the typical numbers you have power rails for any application SoC. Is that?
No, this is kind of
It's just a sample.
example.
Okay.
So actually we have some of the SOCs
Because
that we have-
I mean, honestly, the power rails that we saw were more. So I was just wondering.
This just for representation purpose,
Okay, representation.
but we have like, at least I've seen like 40, 50 power rails are running. in
That's the
parallel.
number I was 65.
Yes.
So
Yeah.
I was wondering, I mean, is it overly simple? Okay, that's fine. Okay, second question is on the verification, the different level RTL. Do you do actually netlist verification with UPF gate level verification?
Yes, yes.
Okay, so you fully run the verification?
No. So it's not full actually. So let's say if you're running 1,000 tests on RTL, so we may run some 100 tests on the netlist
Mhm.
because there are cases where formal check is
yeah.
not closing completely because the exceptions, the waivers comes from the logs. It's still a manual review and sign off.
Right, right.
So people will overlook it and then they sign off. So that's where we have a sample space to make sure that we cover all the power switches at some minimal suit on the netlist to give the confidence. So it's a higher confidence.
Yeah. And the last one,
Yeah.
you mentioned the application of formal for the power state transition.
Yeah.
Don't you need an invalid transition list from architecture to do that? Otherwise, you will run into a lot of incorrect, or false failures, right?
Yeah, so right now, so what's happening is that power state table is kind of getting constructed. We have a nice flow to create the power state tables now.
Okay.
So all possible power states.
All valid ones, your
Valid
invalid you
ones,
already eliminated.
We already have.
Okay.
So only problem is how do I formally prove that all states are covered? As of today, we are creating a SV assertion. We are binding in the simulation. The entire suit runs, you get a coverage and see that, okay, all transitions are covered. Some things are not covered, add more test cases, right? It's a very cumbersome exercise. We have a formal way to ensure that we are exciting all those logic and we are covering it. That will be a very good value add for us.
Thank you.
Swanand.
Hello. Thank you for the presentation. It was really interesting. So I have a couple of questions. So first question I have is when you talked about the DCVS technique, right?
Yeah.
Where a constant feedback is provided to the PMIC so that you can switch off the power supply, right? When the activity is less compared to an average power which is maintained for each and every component.
Correct.
So there is a trade-off, right? Because you have to constantly communicate with the PMIC and you have to also do switching activity, right? You have to switch off and switch on. So compared to the average, right? Have you guys done that kind of analysis that whether that technique is much better compared to maintaining average power to the components? So I mean, what are the advantages?
Yeah, definitely. So it is, even though it's shown as a continuous, it's not a continuous communication.
Okay.
So because you have these sensors in your system, so there is a continuous monitoring happening inside the device. But when there is a tipping point of that you are crossing a limit, that is where we take a decision to go back to PMIC, say that it's going to cross your limit. Now you reduce your voltage and internally we take care of your clock frequency and everything. So if you look at the time scale, there will be a spurious spot where it comes. There is a request to PMIC which controls it,
Okay.
but it is not going to be a continuous because
Okay.
it's not very efficient.
Yeah. Okay. So next question is follow up to the previous question, right? When we talk about PAGLS, right?
Yeah.
So you said you run a subset of tests, right? Which you run for the low power verification at the simulation end. So what kind of issues you encountered in PAGLS which are not caught in low power simulation? And what are the debug techniques you adopt to identify the root cause of the issues compared to low power?
Yeah. So it's always a debatable topic. Do we really need to do the PAGLS or not? It also depends on the backend flow maturity in your ecosystem. So we hit issues where the cells are getting inserted when it's crossing the domain, when DFT overlaps. You put a wrong cell with a wrong power net. So that is, you are not going to catch those in RTL. So center around the power switch where the DFT overlaps, you want to focus on those areas where we can find any issues. Other one is based on your power profiling. You have a single switch which is controlling a cone of a logic of an IP, but that is not working well for the backend cycle. What they'll do is they duplicate these switches and they partition your logic and they kind of connect smaller subset of digital logic under those cones. So when they split from one switch to the multiple switch, there is a possibility that there is a duplicate or a combo kind of switch is getting created. So sometimes you run a power switch focused test case in the netlist, we are able to find such issues. I would say in a typical standard like PARTL, if you're finding 100 bucks, PAGLS you may find some 3-4. Sometimes you may not find also. But because there are issues we are finding and it is very critical if you get the product out with those issues, we are investing certain amount of time on this area. Eventually, if your PD flow is very robust, statically we are signing off everything, we can eliminate PHLS. Anyone else has any question? Okay, thanks all, thanks.
Your expertise in navigating the intricacies of power efficient design has been invaluable. I extend my sincere appreciation for your insightful presentation. Now I would like to invite Apurva Kumar to come and hand over the plaque to Mr. Pradeep. Thank you. We are breaking for lunch now. Let's have a quick lunch and come back within 2:20 because there are more interesting sessions in the second half. Let's make it as quick as possible so that we have time for more Q&A in the second half. Okay. Let's be back by 2:20. Thank you.
Pensando. 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 Pensando.
Good afternoon, everyone. Hope you had a great lunch. So we commence the second half of the day with starting with a technical talk by Mr. Achyuta Kiran Kumar sir. So formal verification, being the rigorous mathematical approach that it is a robust and exhaustive approach that, unlike traditional testing methods, can ensure that there are no corner cases overlooked during verification. A huge feat in the world with increasingly complex designs, and a feat that simulation-based verification cannot commit to. Formal leads to early error detection and enhanced design reliability. But as it stands today, it faces challenges in scalability, usability, and integration. Despite these challenges, however, it remains an essential tool for modern chip design, ensuring the quality and reliability of the electronic devices that power our world. One might even say that formal is the new normal. So on that note, we have Kiran sir, who is a homegrown Intel fellow, joining as an RCG from IISc Bangalore. He leads the Formal Verification Central Tech Office in the Product Enablement Solutions Group. He's recognized as an industry expert in FV and is responsible for defining and executing FV on IPs and SOCs from all Intel design organizations. In this role, Kiran sir strives to increase the formal footprint through various phases of the design cycle. He has co-authored a very popular book titled Formal Verification, an Essential Toolkit to Hardware Designs, which is referenced in university courses. He has 1 patent, 15 Best Paper Awards, and 100+ publications. We welcome Kiran sir to the dais for his talk.
Okay. I have my first. Hey, thank you organizers for actually setting up me to sing lullabies to everyone, right? So just post lunch and that too a topic on formal verification. So it's interesting. I don't know. I think Slobona has something against me. The timing looks like very interesting. So I'll try my best to keep you awake. So I mean, in order to make sure that this is interesting, I would like to actually keep this a little bit more interactive. So if you guys have any questions, please feel free to stop me in the middle, and we can have a conversation there, right? So just to explain what formal verification is, right? Because someone was saying that, sir, people are talking so high level that these are like Shami's bouncers, right? So I said, okay, I'll try to be the lungi ingdi of right, and I'll try to be as low as possible. Let's try to understand a little bit more, right? So before we get into what are the nitty-gritties of what formal verification can offer, right? So as you know, this is again our Intel architectures, right? I mean, you've been studying in all your undergrads and all, where we used to have, I mean, it starts with 4004, and then it is, when as the design actually gets more and more complex, right? I mean, we started designing with schematics, then it expanded to the HDL. Uh, Raj was saying that, right, when Verilog was introduced, right? I mean, it was earlier the design was with all schematics. You used to have people drawing the schematics and then connecting and then trying to test on the schematics, right? So that was very tough. From there, the next level of abstraction came up where we were trying to code everything in Verilog and trying to prove designs in Verilog, right? So then you had a set of blocks that you could actually verify at that point. Then it got a little bit more interesting with Core to Duo, where you have two cores which are integrated into one form factor. Then we went into the 2D chiplets, like saying that you could actually have the compute die in one area, all the memory into one other disk, right? One other die, and you could actually have two dies which are again connected together, right? And then we talked about the 2D chiplet, like you could actually create chiplets, right? The way how we have small blocks, you could actually create chiplets. Instead of connecting them on a PCB, you could integrate everything into the IC, right? So that's the 2.5D chiplet. And then in the Lakefield, that's when we created the 3D stack. Lakefield was a processor where we could create a 3D stack where you could actually have one die particularly on the memory, the base die, the compute die, the connectivity die. There are multiple dies. And if you look at it, when you could actually validate certain design which is all in one place, it is a problem by itself. But when we are talking about things that are connected across the dies, right, and you have to verify the flows across these dies, tell me how difficult it would be, right? Because the flows, the kind of connectivity that you are talking of, the kind of interactions that these guys would have, it becomes a lot more complex. And guess what? This is going to be the future. Going forward, it is going to be the chiplet architecture. You are going to have the most complex features and the most complex dies all over the place. Suppose let's say I don't like this IO die, I'm going to remove this, put some other IO die, and then create a chip for you, right? So that's the future. And going forward, we are also talking about this 2D plus 3D, a large number of dies in monolithic, where you could actually mix and match, and then you could also have a 3D stacking, right? So that's the Ponte Vecchio, which is in the market now, right? We call it as a PVC. With that, Intel has created the Aurora supercomputer AI chip, which is equivalent to multiple H100s and 3100s, right? A100s. So So going forward, what you see here is these architectures are becoming complex generation over generation, right? And which means the verification becomes even more tougher for us, right? So in order to meet these, you need to have a robust technology. And other point that I would like to actually bring this one, thanks to Harry Foster. This is from the Wilson research, right? Where if you look at it, work this one, okay. Oh, LED doesn't. Okay. Okay. So if you look at it, right, how many chips have the first success? Right? I mean, as soon as you type in, there are very less number of companies. I know some of the companies are here, but there are very less number of companies where your silicon gets successful over the first tape in. When even at Intel, we did it a couple of years ago. Now we'll come back. But number of steppings, so let's say 2 steppings. How many of the chips actually go out onto the customer with 2 steppings? You see, there are almost like 50%. Almost half of the chips need one more respin. You know what is the cost of one respin? They give the number? No. Okay, anyone can guess? Cost of a respin? How many $1 million? Sorry? What did you 60? No, you are from Intel, I don't listen to you. It all depends upon the company, right? I mean, what the kind of complexity that you are getting. Anywhere between 40 to $400 million. It all depends upon if someone is designing a small chip, but it might be with $40 million. But if it gets more complex, that's what it is. I mean, it starts with $8 million to actually almost $400 million, depending upon the complexity. So let's say on the PVC, where I have 2 different chips on 2 different dies, right? And if something goes wrong and I have to tape in the whole stuff, obviously it will be expensive, right? So the complexity of your every stepping goes more, right? And depending upon, I don't want to name a company who has just released a chip yesterday. Okay, they went to G steppings, A, B, C, D, E, F, G. Okay, you know how many? Of course, that's a cash-rich company, and they can afford to do that. But then you know, this is not acceptable, right? Do you think the company will be happy stepping in 7 steppings, 8 steppings? No. So which means you need to actually make sure your design is really robust, right? Whatever that you are taping in is strong enough that you are not going through the respins. So, and these are the mask costs, wafer costs, and all that stuff, right? So most of these designs have multiple steppings, which we wanted to avoid. And how do we do that? We will come back. I'll come to the solution, right? But then when we are talking about what is the cost of fixing a bug, cost of fixing a bug in the sense of, well, let's say, a lot of people say that, hey, you know what, the designers and the architects code the design. From the verification side, we said they code the bugs, right? While designing, they code the bugs, and thanks to them, because they code the bugs, we have a job, right? Because we can find the bugs, so which makes our life more interesting, right? And while coding, suppose let's say if you find a bug while coding, the cost is something like $100, and if it gets while doing the IP small IP verification, it is 8x, and if you are doing at the integration level, it is 24x. You'd be wondering why, right? Because when I am designing, I am writing the code and I am fixing it. Company is paying me some dollars, right? And I am fixing the bug while the time that I take, because for every hour I am paid some amount of dollars, and the amount of dollars that you take to code the bug as well as fix the bug is that 1x. And you code the bug, someone else finds the bug, and at a much higher level at the IP, it is expensive. And if you are going for the integration, it's even more expensive. because the integrators have no clue what you have coded, and there is a failure, and they have to debug, call everyone on the board. You know what I mean? In small companies, it takes easy, but in big companies, you will have 10 meetings to find a bug. Right? And all these meetings, you are actually wasting so many hours of time. And all these accounted, that's the cost. And then when it goes to the system validation, like you're talking about the emulation, FPG and all, right? It's even more expensive. Once it hits the silicon, that's it. You have actually written everything on the stone, right? Now you got a failure part. You have to debug, you have to again fix it, you have to go for a respin. So these costs are very, very exponential, which is what we want to avoid, right? That's the need of verification engineers. When I spoke in the morning talking about like verification engineers are the future, you know why they are important? Because we are creating more and more complex designs. With the more and more complex designs, we are creating more and more complex bugs, which cannot be found through any traditional methods. And in order to find these, you cannot have the same mindset with which you have coded a bug. You need a different way of proving that the design works, right? So that's where the techniques called formal verification come into existence. So I come from a team, I started a team called Formal Verification Central Tech Office. We have around like more than 100 formal experts, and then we drive the formal verification across all the products, the clients, servers, graphics, everything. Okay, and again, right, so this is the other way of actually projecting what kind of bugs that you see, right? What you see here is during the architecture, right, when you are creating the architecture, you'll get a lot of these architectural bugs. And guess what? How much time does it take for you to expose an architectural bug? Any guess? How much time does it take to find an architecture bug? Complex architecture, or what is the maximum time that you could actually find an architecture bug? 6 months? 6 weeks? It is 6 years, guys. 4 to 6 years. And again, right, I'm talking from the Indus perspective, man. Some people will not agree with me when they tape in every 3 months, right? So there is a difference. So for us, the life is simple, okay? We do very complex stuff and we take 3 years to design. So even if we get to the design and then get to tape in, we take at least 2 more years to architect it. So the architecture, someone who has architected a bug, I mean, the feature or the bug, right? It takes almost 5 to 6 years to get that exposed, and sometimes the customers give us the feedback saying that, you know what, you have an architectural bug here, which is very, very expensive, right? And then the architecture, from the architecture phase, you go into the microarchitecture, saying that, Ray, so how do I divide into multiple IPs? What this memory subsystem should do? What this IO subsystem should do? What should my fabric do? Right? So you are micro-architecting those details. That's your micro-architecture phase. And then you design, you code all these bugs, and you validate them, and then you get into the silicon, and then again debug the post-silicon bugs. So there are like too many bugs over a period of time, like tens of bugs, thousands of bugs from the concept till this, right? If there are the other thing, right? So in a typical life cycle, again, this is coming from Harry Foster's research study. So what he says is, again, right, I'll ask you a question. How many lines of code would be coded for a say medium set of architecture? Can you guess? For a medium architecture, right? I'm sorry? 20 lakhs. And you should thank that guy who was coding those many lines. Most of the times it's incremental, right? So hardly there will be around like 20,000 lines that will be coded. And guess what? For these 20,000 lines that they have coded, how many bugs would be there? I'm talking about a medium size design, right? For 20,000 lines, you will get at least 2,000 bugs, right? 2,000 bugs. And out of these 2,000 bugs, there will be 200 bugs which are reserved for post silicon, right? So these your costs are so high, right? So these number of lines, you're coding these number of bugs, which actually gives us a lot of jobs, guys, right? So we should thank all those guys. By the way, I mean, jokes apart, right? So I think I somewhere, right? So what do we want to do? We want to actually limit these number of bugs that are going in. And the way how we want to do is you should use all forms of verification to actually prove this. And one such form of verification is formal verification, right? I'm not saying this is the medicine for all those problems. No, it is not, right? It is good in certain areas. It is really helpful to avoid the bugs right from the beginning, and it is very, very helpful to clean the bugs while you are designing, and also making sure that there will not be any more bugs, right? So there is an analogy that you should think about, right? So when you get into the ground, right, when you get into the ground, you might choose to play football, you might choose to play hockey, you might choose to play cricket, you might choose to play a lot of these things, but the ground is same, right? And in order to play hockey, you cannot use a cricket bat. Similarly, to find all your solutions, you cannot have one methodology that can do everything. At one point of time, we were saying that DV is the solution for everything, I mean, dynamic verification. Simulation is the solution for everything. But still, you will not be able to do, right? You will not be able to cover everything. So that's where then we went into the emulation, like getting into the FPGA, getting into emulation, all that stuff, right? Again, it is still dynamic, because what I can think of, I'll write them as test case and I'll try to prove them. Again, there are limitations, because because you have a human intervention, you are trying to apply your thought, and you are also human. People who have coded, you have a similar IQ, you will also code, you might also miss the same kind of bugs, right? So that's where this methodology, which is called formal verification, can be very helpful. So here we try to create what we try to do is we try to map the design into, I'm trying to simplify it, but don't quote me, man. I know there are a lot of professors who are very, very formal savvy. I'm trying to simplify it to an extent. You try to translate it into a graph, or you try to synthesize it into some form where you could actually use some mathematical techniques to prove whether the design is proper or not. Okay, just to motivate you a little bit more, right? Suppose, let's say, I guess most of you are designers, right? At least you know how to design, right? So suppose, let's say, if there is a 10 input gate that you are creating, in order to make sure that the gate is completely verified, how many simulations do you need? Sorry, 2 to the power of 10, right? Very straightforward. And we have multipliers, which is suppose, let's say, fuse multiply add, which is and we are talking about double precision, right? A into B plus C in all your machine learning algorithms. That's what you have, right? When you have you do what do you say, DPass, which is like dot product. You have matrices, you multiply matrices. At the end of the day, that's what you do, and you have a double precision. And we are talking about one multiplication. One multiplication of two double precision numbers. What is a double precision? 64-bit, right? And A into B plus C, which is 2 power 64 into 2 power 64 into 2 power 64. 2 power 192 combinations, if you have to completely exhaustively verify it. 2 power 192 combinations with your simulator speed, which is around like 5 to 10 hertz, will take time for us to go to moon and come back to completely validate it, right? Which is impossible. And in our current designs, we have so many such multipliers, control logic, FSMs, and all that stuff, which will span to such huge state that you will not be validated through any of your simulation methods. But then when you slice the problem and prove it mathematically, right? If you can prove that A into B plus C, throwing some symbolic variables onto it, and through some techniques, if you are able to prove that this is a multiplier, irrespective of whether it is a half precision, single precision, or a double precision, wouldn't the life be very simpler? That's what formal verification does. Okay, this is in very, very layman terms. Shobhan, you have to excuse me. I know she has done a PhD there, right? So, in a very light terms, this is what it is, right? You try to model the design in a very high level graph and try to apply properties, right properties, to make sure whether these properties adhere to the specification all the time or not. That is formal verification, but in very simple terms. Oh man, I don't know. Okay, so formal verification could be applied in various areas. Again, there are two different areas in application of formal, right? One is to create the logic around it, in the sense how can I prove the design, right? So that's an algorithm which actually tells how do I prove a multiplexer, how do I prove a FSM, how do I prove a multiplier or a divider and all that stuff, right? So those are mostly into the algorithm part. We call them as engines. And the other part is application. Where do I apply formal? How do I apply formal verification to solve a design problem? I have a complex, suppose let's say arbiter, which says, I'm trying to arbitrate, like there are like 3 different people who are trying to arbitrate, and there is one resource where you are trying to map to. So what I can write a simple property, whenever I apply a request, eventually it gets a grant. That's a good property, simple property for us to learn, right? So we write those kind of properties on the designs, saying that, you know what, for this kind of behavior, I would expect so and so behavior from this particular design. So in case of this scheduler, I say that eventually my request will go out, right? Eventually someone will get married. So people cannot be happy all the time, right? So they need to get married. So even that's the kind of properties you write. You say that I will write a property and try to prove it on the design. So that's the formal property verification. So this is the application side of this, and there is one particular area which talks about how to prove this particular property, how to slice it, what kind of graph traversal it should have, how should I even represent a system. So that's a different studies. So Professor Pallab in the morning has talked about the various automata and all that stuff, right? I mean, LTL, CTL properties, all that stuff, right? That's the PhD kind of term. And for us, for laymen like us, we have the application. Because unless you connect the application to this, there is no use of this cool technology, right? Unless it is very similar to AI. I was talking to someone over the lunch, right? Even in the AI, there is a way how to create, whether it is a regression method, whether it is a supervised learning, whether it is what do you say, what sorts of learnings, what sorts of algorithms that you have, right? Random forest or whatever it is, right? So you have someone who is designing all that stuff. But if there is no user how to use an AI, luckily with the ChatGPT, right? Everyone knows now AI is the buzz, right? Unless you use it, there is no use of how much you do, right? All the neural networks, I mean, neural networks has been studied for the past 20, 30 years. But till someone applies it on the application, it is not useful, right? So that's where the industry is looking for the application, not only on AI, it is also similarly the same concept even on the formal verification. You have to apply formal verification. And these are the various areas where you can apply formal verification in a design cycle. You could start applying at the architecture, at the specification. While you are writing a specification, you could actually use formal techniques to prove whether the spec is clear or not, or whether the spec has any holes in it. Whether, for example, whether there is if I'm designing a protocol, would my protocol always go to, would my state go to the next state, or will it get stuck somewhere? When you are talking about a cache coherency, have I taken care of all my cache coherency states? Do I actually transition, right? So those are the ones where you could actually apply formal techniques to prove your spec. And even at the architecture level, you could actually have tools to prove the architecture. There are a lot of academic tools, and there are a lot of, we are coming up with, partnering with some industries to come up with industry tools to prove the architectures. So that's the architectural formal verification. You could prove the architectures where you will find a bug somewhere after 6 years, you could find it in less than 6 weeks now, right? So that's application of formal could be done right from the spec to the arc to the RTL design, right? At the RTL, when you're designing the RTL, you could actually prove whether the design works or not. Or you could actually have some auto formal checks. Professor Palab has talked about it in the morning. So you could actually write some tests, linting checks and all that stuff that could be used there. Formal property verification, which I talked about, and data path verification, which I was talking about, those multipliers, adders, dividers, all the machine learning algorithms, all right. That could be using the DFV. So, and then you could actually, once you get into this verification phase, you could do a complete verification of your design using C2RTL or STE or security verification. At the SOC level, you try to make sure that your connectivity is proper, whether your low power is working properly or not, whether the FSM for your low power is working properly or not. We have solved that problem, by the way. You can hire me. Just kidding. Right? So there is a way to prove the low power. There is a way to prove the control registers. There is a way to prove all your properties on your control path, the data paths. Everything could be proven. When formal could be scaled to solve any of the problem. If there are certain problems which you might not be able to completely solve it, but that's a challenge, right? And that's where we would want to add our value, right? By the way, we've been also working with this industry and as well as academia. For the past 10 years, I think we helped create at least 6 new tools from our team to be used in the industry. So there are a lot of tools that you could actually work with the vendors to create these tools. And then there is something called a formal equivalence, which could be applied even at the RTL level as well as at the physical design level, from your RTL to netlist, whether these are equivalent or not. And then once you get into the silicon, right, already the bug is there. But there is, again, right, I'll ask a question. On an average, how many weeks do you think someone would take to reproduce a post-silicon bug on a medium design, on a medium complex design? Any guess? Which company you are, man? Right, so I will tell you again, I am referring only to Harry Foster. I cannot reveal anything about Intel. I can only refer to what Harry Foster has presented. Anywhere between, I mean, it all depends on, I am talking about the medium complexity one, right? So again, when we are talking about the medium complexity, anywhere it can, to reproduce a bug on the silicon, what you have seen on the silicon in your pre-silicon environment, it can take anywhere between 4 to 40 weeks. And I have seen personally bugs which are open for 40 weeks. Not in my company, in some other company. Right? So we have seen that. And we have seen people who have been reporting that, which means 40 weeks is almost 1 year. You're sitting on a bug for 1 year without reproducing, right? Shame on it. But then there is a way to actually reproduce that bug much earlier using formal verification. And there had been papers from ARM, there had been papers from Samsung and NVIDIA, where even they actually talk about these tens of weeks, right? Where they were able to actually pull in, reproduce within a couple of weeks. And we have mastered the technology. We call it as reactive formal, because whatever that you do before the chip tapes in is proactive formal. What you do after the chip tapes out and you see a bug is called reactive formal. So in a nutshell, formal can be applied right from the specification to the silicon verification, right? So you can use formal all over the place. That's the reason why we say formal is the new normal, right? If your company is not using it, push for it. Push it. I want you to be the evangelizers of this technology. For that matter, when I was trying to evangelize this, no one really trusted me. But today, there was only one fellow from, till yesterday, till last week, there is only one fellow, at least in Intel, fellow is something like the topmost technical achievement. There is only one fellow in the whole Intel, India, out of 15,000 people, and that comes from formal verification, which means it is your perseverance which actually takes there. The technology is very, very strong, right? And I want you guys to, if you are not on FE, come to FE. You can create your own careers, right? The careers are going to be very, very rock solid, strong. And for all the students who are trying to see what could be your next goal, get here. By the way, we are hiring. Okay? And then, again, right, here, from these, we call all these methodologies where we say, ideally we want to code less bugs, but that's not possible. So we will try to find bugs early and also keep those bugs out, and also make sure that we are making sure that whatever the workarounds are always proven, right? So that's the promise of formal verification, right from the architecture to micro arc to the design, where you could actually use this through the complete gamut of your design cycle. Formal is helpful, right? So with that, I will not talk about this. Again, right, I talked about this a little bit more. And this is the recipe for, I just wanted to touch upon one of the areas which hasn't been explored or exposed more in the industry yet, or in the academia yet. So that's the reactive formal, which is the post-silicon formal, right? So what you could do here is, this is a recipe that we have applied for a patent. We'll have to see, but I'm talking about it, right? So where we are talking about, like, you could actually see what could be the failure, right? See, all the other areas, you could always find some papers here and there. This is one particular new set of formula which is coming up new, and trust me, we have used it to verify almost more than 50 post-silicon issues in this year in various designs. So the way how we do this is, we actually take out all the dumps, collect all the essentials, collect the design information. But what happens in the post-silicon is, you get a hang. You don't know what that hang is. Some design just hangs. And then when you debug, when you have the traces from those, collect all your performance monitors, EMONs, PMONs, EMONs, everything that you collect, and you find out that something is not actually reacting in time, or some guy is stuck. Then you think, okay, it could be a problem of this particular subsystem, right? Then you try to apply some more tuning, and then you find out. So anyway, I think my next speaker is going to talk more about the post-silicon formal. I would not go more into it. He'll tell you, at least he will tell you what are the problems he faces or he has seen from the post-silicon front, right? So trust me, guys, it's not easy. Pre-silicon bugs finding is much easier. Debugging is much easier. Post-silicon is, you need a different mindset altogether, right? So getting that, trying to find out where that bug is within that subsystem, which IP has the bug, is like finding a needle in a haystack, right? And then you get to that IP, and you don't know within that IP, there are like 10 different blocks. You don't know which block has created the problem, and you come up with like 5 theories, and you try to replicate in the DV. So what we try to do here with the formal verification is, take all those essentials, brainstorm the property that you think. Suppose, let's say, if it is in the scheduler block, it is not fair in transferring the request. So let's say you could write a property. You could write the property there, and then try to see what is the starting point. Most of the times your starting point should be the trace that you have got it from the silicon. Take that as a starting point, and then start exploring more into the state space. Try to prove the property, and definitely you will get those failure. Then you try to balance the constraints, because formal needs some constraints, right? Tune those constraints, and make sure that you create an environment, take it to the pre-silicon. this is the way how we have been doing this. And then we are very, very successful in reproducing the bugs faster, as well as proving the bug fixes that they are not going to create another slippage. Okay. And with that, there are a lot of these things that you could actually see that formal could actually do a lot more stuff. We are trying to also work on something called, which is where you could actually create a formal test bench out of a dynamic test bench. This is another research activity that we are doing and we are 50% successful on this, where we are talking about you have a lot of these dynamic environments on all your designs. How about if I translate that into a FE environment? Today, if I have to write an FE environment, it will take anywhere between 6 weeks to almost like 1 quarter. I could actually left shift this, and with the methodology that we are currently working, I should be able to translate everything in 1 day. Complete dynamic environment to formal environment. Currently, we are 50% done. We'll be doing more on that. And then the next call for the collaboration that I would like to leave with this thought. We are working with Synopsys on this. Dr. Pallab has mentioned this in the morning. You all heard about a term called UVM, right? What does UVM stand for? Not the industry guys. Methodology, right? So now everyone uses that UVM. When it started with something else, everyone uses that UVM, which is a standard methodology. But today, if someone has to use a tool, Cadence has a different way of dealing with a problem. Synopsys has a different way. Mentor has a different way. OneSpin has a different way. We want to stabilize everything, and then we want to lower the barrier of entry into formal verification through this methodology, which is called UFM, which is Universal Formal Methodology. Right? Anyone interested? It would be great for us to partner with you, both academia and the industry. We are going to create a consortium across all the industry. So let's join the bandwagon. Let's tell EDA what to do rather than them telling us what to do, right? So let's turn the sticks around, right? Okay, and sorry, man. Okay, so that's where I would like to leave it with this at this level. We can have a deeper, more tutorial at some other point. We're going to start a formal club soon. We're discussing with some of our folks, right? So we'll create something like this, and we'll have more discussion about it. Thank you. Thank you for staying awake, guys.
Agree that the lullabies failed because you kept us all awake. And on a more serious note, I think it was a very interesting talk where we were able to appreciate that formal today is being integrated into every stage of the life cycle, right from architecture until post-silicon. So thank you, sir, for that engaging talk. I now invite Mr. Jayesh Tanwani from the IEEE CAS Exicom to hand over a token of our appreciation to Kiran sir. So our next technical talk is going to be on enabling smarter pre and post silicon validation strategies for SOCs. Our speaker is Mr. Nilesh Dhavlikar, Senior Director of Engineering at Qualcomm. Mr. Nilesh has 20 plus years of industry experience in the VLSI industry, and he has developed expertise in SOC pre and post silicon validation. Currently, he's leading and managing SVE, SOC validation and emulation team in Qualcomm for the Snapdragon mobile SOC chips, driving overall SVE execution and enabling successful commercialization of chips used in mobile handset, compute, automotive, and adjacent markets such as IoT or XR. Nilesh has leadership experience in setting up large teams with a mix of fresh and experienced SOC, emulation, and validation engineers. And he is passionate about improving overall pre and post silicon validation methodology or flow and driving the debug of complex post silicon issues. Nilesh holds master's degree in electrical engineering from University of Nevada, USA. Over to you, Nilesh, sir.
Okay, so good afternoon. I think very good speech from my earlier speaker who talked about formal. So I'll also try to keep you awake, and I would like to make this session more interactive. All the experts before me, they talked mostly on the pre-silicon, right? Pretty much all the challenges what we have in terms of formal, low power, simulation. Where here I'll be slightly switching the gears, and my focus is more on the post-silicon side, right? What are the challenges we have in the post-silicon? I mean, as my earlier speaker spoke, right? As we do go from pre to post, the cost of finding the bug is very high, right? Whereas if you go to post silicon, any bug which you escape, right, and which goes to customer, can anybody guess what will be the cost involved? Let's say I have a chip which I'm designing for a smartphone, or let's say for a laptop, and let's say I ship that faulty chip to the customer, and then the customer returns that chip to me and saying, hey, your chip is faulty, right? Then what is the cost? Can anybody guess? What we called as an RMA, right? The RMA unit which comes back to our company, which is returned by either the OEM or customer. I mean, the cost is as high as if it's going into a smartphone, then pretty much we end up paying the cost of a smartphone, or if it is for a laptop, right? Pretty much you have to pay the entire cost for a laptop. That's why post-silicon is very critical. Again, the challenges, what we see in post-silicon are entirely different, because post-silicon, I mean, the biggest advantage is, anything you run is much, much faster. Simulation, right, to get a result, you have to wait for a days, weeks, anything. Whereas post-silicon, immediately you have the results available. But what is most challenging is the debug part. Because silicon, if you see today, is like a black box, right? So what are the challenges those we have in post-silicon validation? What are the methodologies? What kind of debug hooks? And how do we, based on all the debug learning, how do we give that feedback to the design, right? To improve the design for debug. So all those key challenges I'll be covering. And at the same time, I also want to focus the different methodologies what we use, right? Because as we diversify, right? Today, let's say if we are doing a chip for mobile, but once we go to auto, or go to AR/XR, or we go to compute chip, each segment has its own requirement. For example, when I go to smartphone, we talk about DPPM, which is defective parts per million. But if you go to the automotive industry, right, they talk about defective parts per billion. That means, let's say, and the requirement is it has to be like a single digit, right? When we go to auto industry, you cannot afford, let's say, if you have a self-driving car and if you have a defective chip, right? So there the DPPM, instead of DPPM, it is DPP billion. So the requirements are very stringent. So I'll talk about that, what kind of techniques or strategies we need, right? Especially for all these adjacent markets, going into compute, going into auto, going into IoT and XR, and what kind of strategies that we need to evolve, right? Both in terms of pre-silicon as well as post-silicon. I mean, pretty much, I think our main Qualcomm main theme is enabling intelligently connected world for everyone. When we say the connecting, right, it includes everything, through smartphone, through tablets, through all the different IoT segments, the AR, XR, wearable devices. Right? And then connected intelligence age, again, it's all focused on the wireless connectivity, We are talking about all the high performance core, right? The CPU cores, DSP core, neural processing engines, and of course low power, as Pradeep said, right? Again, we have a different challenge. And of course the on-device AI processor, right? With all the ML and machine learning capability. So how do we do the comprehensive pre and post silicon validation for such chips, right? Where we have a very high complex cores, all the processing powers, and also the wireless connectivity, right? Which includes the modem, Bluetooth, and also some of the RF challenges we have. So I'll talk about that. Again, these are the opportunities for innovation as we are diversifying our portfolio and looking into more into the automotive, consumer IoT, and the industrial IoT, right? So what are the opportunities we have? Because if we have to develop the SoCs, right, for to serve this or cater this different market segment, what are the strategies that we should be focusing in terms of both pre as well as post silicon validation? Because each segment you see, right, the complexity level, the feature requirements, and even the post silicon side, right, some of the features, some of the requirements what they have in terms of performance, in terms of power, in terms of thermal, in terms of defect density, those are entirely different, right? Again, intelligently, our goal is to basically connect the entire world and at the same time focus more on innovation, right? Where we start looking at the new methodologies and how do we cater all these different industry segments, right? Including IoT and infra and all the adjacent market, including the wearable products. Again, going back to our vision, right? So main thing is we want to build a high quality, and again, not just the core, but core to SoC. And one of the segment which one of the things where I'll focus more is on software development, because today you see, right, all the different chips we are using, how early we can enable software, because software, unless you run all the end-to-end use cases, you make sure all the mission mode software you can run the actual or either pre-silicon platform or post-silicon platform, that plays a key role, right? Then only you can enable your product to the customer. And for that, we need a robust validation content. One is the functional validation, because you want to make sure your silicon is bug-free, and also focus on the performance and the low power mode. But all these things, again, a lot of work is needed in the pre-silicon to ensure that you don't spend a lot of time in the post-silicon, right? When we start doing the post-silicon validation. And of course, as we go into post-silicon, see, it's not just I want to validate on 2-part, 3-part, right? Whereas I want to make sure I do the volume testing, right? Because when you go to silicon, you have all the different type of silicon, what you get, silicon material you get, right? Starting from a slow material to your typical and going to fast. So you want to make sure all your content, everything, all your mission mode should run seamlessly on the volume parts, right? Because again, as we go, the process tech node is shrinking. We go to 4 nanometer, 3 nanometer, 2 nanometer. Again, the technical process wise, there are more and more challenges. So that's why in post silicon, it's very important you develop the validation and methodology flow where you can do the testing on the volume parts. And it's just impractical to do it a manual testing, right? And for that, what you need is an automated handler, what we call the SLT handler, right? Where you can test like thousands of devices at the same time, right? Using a robotic arm, which will pick up your silicon, which will put it on that. You run all your test bare metal test content vectors. You can boot your Android. You can run like different type of benchmark, right? So you need an automated handler which can help you in doing the testing on the volume parts. And of course, one challenge I said, right, as post silicon is like a black box, right? You're debugging. So you have to improve your debug methodology, right? Because let's say, I think earlier we mentioned some of the bugs which we find in post silicon. If you have to reproduce, it can take like several weeks or several months, right? So how fast you can debug those issues on post silicon, that is one area. And for that, how do you reduce this turnaround time, right? Because sometimes some issues take like long time to ideally root cause and see where the problem. So how do we debug those issues faster on post silicon? And of course, DPPM I talked, right? Again, because this is a very critical requirement when you ship your products to customer, right? They don't want to see the defects in the silicon. So how do we reduce those DPPM defects, and what are the post silicon methodologies we should focus to reduce this DPPM? So here, I think just a very high level, As you grow from architecture to design verification to PD to fab and post silicon, what are the different platforms and what we have, and where is the right usage for those platforms, right? For example, architecture, I think earlier speaker, we focus more on TLM models, which is a system C model, to make sure your design is working as per the spec what you have designed, right? But as you go more into the core block level or SOC level, right, we focus more on the design and verification. Where RTL simulation pretty much we cover till the tape out, but we have something called a big box emulation. People will ask, hey, if I'm doing simulation, why do I need this big box emulation, right? Because again, simulation has its own limitation. Typically, the performance what you get is like in hertz, right? But whereas we go to big box emulation, we have pretty much standard Veloci tool, and then we have Palladium where we go from hertz to kilohertz. But at the same time, we have our own custom emulation platform where we can achieve a frequency of almost 50 to 60 megahertz. Today, let's say if I'm doing a chip which is going to go in a smartphone, I want to make sure before I do the tape out, I should be able to run the boot the complete Android, and I should be able to run all my software mission mode use case. There is no way we can do it on a standard big box emulation. For that, we need a custom FPGA solution where I can emulate with the higher, with the bigger capacity FPGAs, right? I have my custom flow and I can run my CPU like almost like 40, 50 megahertz. So that way, if software I want to enable, right, they should be able to boot up Android in, let's say, 25 to 30 minutes. Same thing if I'm selling my chip for a, let's say for a laptop or a tablet, right? Windows should be able to boot, right? In 30 minutes, they should be able to run all the Windows drivers, all the different use cases. For that, we heavily rely on a custom emulation platform where we can achieve the higher performance, right? Especially for all the cores, and you have entire SoC, different mission mode use case. And more importantly, you can enable the firmware as well as the software team. That way you make sure you give a very high confidence before tape out, saying, hey, all my use cases, including my software and all the different performance benchmark, I have run on the emulation platform. And of course, post silicon, again, the spans the whole thing, right? Where you can validate all the cores, SOCs, bare metal, SOE, and pretty much entire OS stack and all the application. That is what you run on silicon. So pretty much, but as you go from pre to post, right, I think where the challenge is grows up in terms of debug, right? Because your debug becomes more and more complex as you go to the post silicon. So what we do when we have to do a complex SoC, right? What are the typical, how do we enable these complex SoC systems? What are the key things that I should be focusing, right? Of course, system level use cases, low power. And then of course, when we go to the silicon, right, we have to do the silicon bring up, enabling software teams. And emulation, I talked, right, in the pre-silicon, the enabling the software, actual mission mode, end-to-end use cases, concurrency scenarios. Those are the focus. And then of course, performance validation, right? Again, that's a key thing. How do I make sure the RTL which I have coded, I'm able to meet my performance requirement, right? Different concurrency use cases. How do I make sure I'm really meeting? So for that, we have a methodology where we do the scale emulation build, right? For example, when I emulate the entire design, normally we do at a certain frequency. But when you really want to do, let's say my CPU to DDR, am I really meeting my performance or a latency or bandwidth requirement? I have to do a clock scaling, right? So for that, we create a clock scale emulation build. And that gives me again, hey, when I'm doing a CPU to DDR, am I really meeting my bandwidth or a latency requirement? So that's how I can make sure all my performance benchmarks, everything, like for example, Antutu is a very standard benchmark. If I have a way on my emulation platform where I can measure, hey, this will be my Antutu score, then that gives a good confidence, right? Hey, even in the pre-silicon, I'm able to do the entire performance validation and make sure my performance goals are met and give a good confidence before I tape out the chip. So this is how we enable the complex SoC systems. And then then again, when we do the overall verification methodology, right? What are the key facets of SoC emulation and validation, right? Emulation, again, we have a big box and we have custom emulation. The goal is enabling the full software stack, running the actual use cases on an emulation platform and make sure my design is robust. And then of course system concurrency also, because a lot of time DV, right, we focus most on the standalone vectors. But if you really want to test the system concurrency scenarios, right, especially multimedia blocks running with CPU, running with GFX graphics concurrently, how do I validate those scenarios? Again, those scenarios are something where my emulation platform will add more value, right, because I can run those scenarios much faster, which I cannot cover in simulation. And same way software, when I start running the mission mode use cases, right, all those blocks I can validate concurrently. And of course, power and performance use case, right, in terms of system low power modes, system level use cases validation, performance and power correlation. So all those things, again, the goal is to left shift, do more and more things in pre-silicon. That way we don't have to debug all these issues on post-silicon. And of course, as we go into post-silicon, it's more focused on the DPPM reduction, right? For example, when you go to silicon, just running at a room temperature is not sufficient. I want to make sure my silicon is functional at cold temperature as well as hot temperature based on the spec what it is defined, right? For example, it's an automotive chip. I have to make sure it has to run from, let's say, -40 to +125 temperature, right? So those are the things that I'll be focusing more on the post-silicon side, right? So again, the key is overall timelines are shrinking because the time from the time you just start designing your chip till you tape out and till you commercialize, the overall cycle time itself is shrinking. So with that, how do I come up with this smarter pre and post silicon validation? So these are some of the key factors that when I'm doing my test plan, right, I have to keep it in mind. Yeah, again, what are the opportunities here when I am enabling this, when we are enabling the complex SOC, right, which is very in the diverse segments like compute, IoT. What are the challenges? Pretty much planning is where you start understanding the spec, you come up with the comprehensive test plan, and then you decide, right, my earlier slide, what is the right platform and right tool I should use. Because again, there is no that with one tool I can do everything, right? For some of my core level, I can do more on the formal and also on the simulation, whereas I go more and more validating my software mission mode use cases, benchmark, how to focus more on the emulation platform, right? So again, choosing the right platform and right methodology at the right milestone, that is important. And of course, the test plan development, right? What are the key things, not just standalone, but I have to look at concurrency, mission mode use cases, system level use cases, and of course, how do we plan these milestones, right, to ensure the quality of the design. And again, the important is we have to keep left shifting, right, because any bug you find in post silicon is very costly. So it is important that all the bugs, we have to catch it in the pre-silicon phase. And for that, we need a very smart optimized test content, right? Because the test content is not good enough, then there is a possibility that you can leave some bug on the table, right? For that, we have to write a very comprehensive test plan, make sure it is aligned, it is reviewed, and it meets the product requirement. And as we go into debug, right, again, this is where a lot of diagnostic tools we need to develop, because today, if you look at any issues comes, let's say your chip, somewhere you see a hang, right? Then again, it's extremely challenging to figure out where exactly in system you have hang. Is it at your CPU level? Is it at your NOC level? Is it like your one of the multimedia cores is not responding? For that, again, we have to develop some automated debug tools, right? For example, the tools which it can give me a visibility, right? Hey, where exactly when my hang happens, which flop is stuck in the design? I should be able to do a scan shift and figure it out, right? And give that information to designer. This is where it's stuck. But again, that will help when you have hang kind of scenario. But let's say sometimes you hit a timeout kind of scenario. How do you debug? Again, for that, you need to have some debug hooks in the design, right? Either through a trace information, or you need to have some kind of an hardware events in the design. And just having that design infrastructure is not enough. You have to develop a tools around that, right? For example, when I'm doing a CPU low power mode, and let's say one of the low power mode, my CPU is stuck, right? I need to have those hardware events, and through tool, I should be able to profile those things, right? Hey, when this scenario happened, this is where my CPU was stuck, right? And this was the last thing instruction that CPU executed. So all that, for that, we need a diagnostic tool where we can really go, and when the failure happens, right, you can get all the meaningful information that will help us to debug and root cause the problem. Because again, post silicon, this is where we spend a lot of time, right? I mean, it's hard, right? You do like 1,000 millions of test vector and one vector on one silicon, it fails. Then how do we debug it? For that, again, there is a need to develop these diagnostic tools, which will really help us in root causing the issue. Again, the goal is ensuring the zero hardware bug escapes, reducing the debug turnaround time, and of course, reducing the number of RMAs, right? So again, we start with the bare metal test content, where you develop all the processors, peripherals, multimedia tests, and of course the full chip congruency test, right? Because some of the issues like, let's say your system timeout or some of the hang scenarios, only when you start running the different cores concurrently, that is where you will hit those system level issues. And of course, enabling the mission mode software use cases, because there is still some no matter how much bare metal or DV validation you do, right? Still there are some scenarios which only when you run the actual software mission mode, those scenarios only, I mean, those tests only can catch it, right? So it's important that we enable a complete software in the pre-silicon itself, right? So that way any bugs which have escaped from DV or with the bare metal content, with software content, we should be able to catch. Again, on the post-silicon, I talked, automated handler is very key thing, because if, let's say if you're shipping millions of parts, then it is very important that each and every part what we ship to the customer, it has gone through my complete validation process, right? And there is no way I can test millions of parts manually. For that, we need a robotic handler where I can run all my bare metal tests, also run all the software-based tests, right? Whether it is Android-based or Windows-based, run some of the benchmark, some of the concurrency use cases, and make sure each and every part which I'm shipping to the customer, right, has been validated. And that is not just at room, but across temperature. Because some of the mixed signal IPs we see, right, even though they work at room, you'll have those challenges like cold temperature and all, right? They're very sensitive. So that is where we focus, where we develop handler capability. And again, here the cost is very important, right? I want to make sure I don't spend like several hours in doing the testing on each and every part. But at the same time, how do I do the parallel testing, right? So I have to develop a handler which has a multiple parts it can check at the same time, right? So that's why the handler capacity is also very important. And of course, the Fmax Vmin, because you will see a process variation, part to part, you will see, right? Whatever performance you get, let's say on CPU, you may not get same performance on every part, right? So for that, again, Fmax Vmin performance correlation has to be done to ensure every part which I'm shipping out, right, is working at the expected frequency and voltage corner. And of course, enabling the bare metal, because again, if you want to debug anything with actual mission mode software, it's very hard. Whereas if you have a bare metal content, debug can be much faster. So that's why it should be complementary, where you have software content running which can help to find some corner cases. But at the same time, if you want to debug something, for that you need to have a bare metal content, right, which can help you to debug faster. And of course, reducing debug turnaround time. For that, again, we have to have a DFD solution. We need a support from the design to add more debug capability, right? If anything fails on silicon, I should be able to debug faster, right? Give the meaningful information to designer or DV how to reproduce. So there is a need to have this sophisticated debug solution. And for that, again, post-silicon is an art, right? It's not that the way you do your verification, you look at FSDB waveform. But in post-silicon, you need an entirely different skill set, right? Because the debug visibility is very limited. That is where we have to form a dedicated debug skill team, which can go and look at silicon, look at traces, quickly analyze and develop the automated tools, right? Based on trace data, based on my, let's say, the Scandum data, I should be able to debug faster. And of course, enabling the content, if customer RMA comes back, right, how faster, quickly we can debug that issue. For that, we have to have a robust validation methodology, right? Again, I talked about the DPPM, right? When we start shipping the parts to the customer, again, DPPM versus cost, it has to be a balancing act. For example, I cannot have a solution, right, where my DPPM is very high. If my DPPM is very high, that means the product quality is not good. But at the same time, I try to make it very, very low DPPM. Then it comes with the cost. For example, let's say I want to ensure my DPPM is like, say, it's a single digit. Then what it means in post-silicon, I have to do more and more testing, right? Either on the ATE tester or on the SLT, I have to check that part for a longer duration. And moment you start testing it for a longer, it adds to the test cost, because whether it is an ATE machine or a standard SLT robotic handler, right, it comes with the cost, right? So what I'm saying, it has to be a balancing act, right? You cannot have a product where your cost time or this thing is very high, right? At the same time, you cannot have a product where your DPPM is very high. So we need to balance it, right? So again, it is important that if you want to reduce the DPPM, we have to improve our SOC coverage. That means in a small, shorter duration of time, I should be able to validate more functionality in my SOC, right? Or a given die. And at the same time, I should be able to capture the unique DPPM. Again, when I say unique DPPM, it can be a functional defect, it can be a timing defect, or it can be a process defect also, right? For example, certain parts, you see certain failure, you will see only on certain parts. So we call it as a process defect. So that again, we should be able to catch it in our in-house testing, because we don't want the defective part to go to the customer. But at the same time, when you start doing this overall DPPM improvement, sometimes you might you might see a false failure, right? It could be a test content issue, or it could be a software issues, right? And of course, you have to reduce the test time also, right? While making sure my DPPM goals are met. And again, industry is pretty much trending to 100% SLT, right? Because SLT is the platform. Again, AT, again, it has its own limitation, right? Where you can run the standard structural test, you can run few functional vector. But when you go to SLT, right, which is an automatic system level testing robotic handler, this is where you can run the actual software mission mode use cases. You can boot Androids, and this you can do on each and every part. So that's the reason we are moving more towards, and as you go to the advanced tech node like 4 nanometer, 2 nanometer, there are more, the defect density is increasing. That's why it is very important that we run all pretty much the mission mode content on the SLT platform, in addition to AT testing before we ship it to the customer. And of course, we have to optimize the test content and also the test time to optimize the cost, because as you go to the production testing, right, the cost is a major factor. Again, AT and SLT, some products, right, you might end up, once your DPPM becomes stable, and let's say I want to optimize my cost, then again, based on that product, we can decide whether AT or SLT, do I need one of them or do I need both? So again, that should be driven by the customer acceptable DPPM. Okay, so now slightly shifting gears, I'm going to talk about a little bit about the automotive and what are the challenges if you are doing the chips for an automotive. Because whatever methodology or strategies we use for a smartphone chip, same strategies may or may not work for automotive, because automotive again has a very stringent DPPM requirements, right? And the challenges are very different in auto. Again, if you look at the car, right, pretty much the entire car is getting transformed, where you have a new generation of automotive and where you are adding more and more ADAS features, safety feature, infotainment features. And again, with the smart cockpit coming in, right, again, there is a requirement to have this immersive infotainment, digital service. So more and more complexity is getting added in the chips, what we design for automotive. And again, that comes with its own set of challenges. So one of the things I talked, right, automotive, again, the requirement, the DPPM is very stringent, because you cannot have a part which is used in automotive, and if that part is a defective, right, then the cost is very high. So we need to have a strategic dimension that ensure that you meet the DPPM targets for the auto. And what are the things we focus before we start shipping the parts to the customer? We have to have a comprehensive AT and SLT testing, right? Because here auto, I want to make sure when I ship the parts, right, there are no defects in that. So we have to have a comprehensive both AT as well as the SLT strategy, right, where we can do both the structural test as well as the actual software based test before we ship the parts to the customer. Low power, then mixed signal IP. I gave an example, right? Let's say PLL I have designed. On post silicon, it might work at a room temperature, but same PLL, when I take it to cold temperature, right, let's say minus 40 C, what if the PLL fails to lock? Again, it is very important, all those mixed signal IP, we have to run those stress content across the temperature, across cold, room and hot temperature. That way I make sure I meet my auto requirement. And of course, the PDN and the limit stress management, right? PDN is again because of the power distribution network. What if there is some noise in the chip, or I start seeing some droops in the chips, right? When I start running a mission mode use case. So we have to have a PDN and limit stress test. And again, the built-in self-test. Example, auto, right? We run all the BIST algorithm. Because every time you start the car, you want to make sure all the logic inside the chip is intact, right? For that, auto is what we run is a BIST, which is a self-testing a mechanism, which will go and make sure my logic, which we call logic BIST, and then the memory BIST, right? It doesn't have any defects. So that way it makes sure when you start your car, right, your chip is fully functional. And of course, volume temperature testing we talked, right? And again, all this we need a right methodologies to improve the overall test time. Now, a little bit, I'll talk about the PC side. So, especially, let's say, if now we have started selling the Snapdragon-based chips, this Windows on Snapdragon, and selling it for the PC segment. What are the challenges we encounter here? And what should be our verification and validation methodology, especially in the post-silicon, to ensure that we are converging this mobile and the PC world? Pretty much a laptop is as smart as your smartphone. And now let's say Windows, Qualcomm is putting a lot of efforts, right, in terms of enabling this Windows on Snapdragon. So what are the typical challenges we see, right? So one of the things you see in the, especially when you go to a laptop world, is the interoperability. For example, if I'm designing a laptop which is working on, let's say, Windows on Snapdragon, which is ARM based, and I want to connect it to an external monitor or a printer, how do I make sure any monitor or any third party, right, it can work? Let's say I just connect it through a USB 4 Thunderbolt. How do I make sure it can work seamlessly? So that is what we call as interoperability and certification, because there is a USB certification community that makes sure when you have a device which works on, let's say, a Windows, this thing, right? When you run all the Windows driver and any external device you connect, which can be a Thunderbolt or which can be a, let's say, external monitor, printer, anything, it has to work seamlessly, right? So that is where when we go to post-silicon, we have to put a lot of focus. Again, there is a USB standard community which defines a compliance test suite that you need to run and you need to pass that. Then only you will get a certification saying, hey, your chip, what you have designed for that platform is USB certified. Again, we work very closely with that USB committee and make sure all the compliance tests, what they have done. When I say compliance, it's not the functional test. It includes the electrical test also, right? Making sure all my, basically my platform and the transmitter, receiver, all the characteristics I'm meeting. That way I can make sure when I run the USB 4 at a high speed, all my electrical compliance is met. And at the same time, we have to examine all the commands, right? Especially in the PC or this PCI or a USB. I want to make sure all the protocols, functional as well as electrically, my chip is meeting the requirement. It's meeting the spec. And of course, as we go to USB, we have multi-lane, right? Or PCI, when we have Gen 4 standard, now we are marching toward Gen 5. How do I make sure my lanes, when I do, I have a sufficient margin, right, across all the different corners? And of course, with all the BIOS interoperability tests. So this is where I think today we are seeing a lot of challenges, right? How do I make sure all my drivers, all my device, all my chip functionality, I'm making sure I pass all the electrical compliance, functional, and also all the different tests what this committee has defined. And again, for that, we have put a very comprehensive methodology where we look at some of the interoperability gaps what we have and to make sure we close those gaps. And at the same time, we have a good coverage to achieve that certification. So this is one of the area as a post-silicon, right? Especially if you're targeting chip for compute and for the segments, that is the one area we need to focus, especially on high-speed interfaces like USB 4 and PCI Gen 4, Gen 5, right? This is what is important. Okay, so yeah, I mean, pretty much I wanted to give an idea as we diversify, right, and go more into the adjacent markets like compute, auto. What are the challenges we have and how we should focus in terms of both pre-silicon, post-silicon validation and ensure that the solution what we are providing to customer is they are robust. With that, I'll take any questions.
Hello. Yeah, so I am relatively new to the industry. It's been 3 years. So is there any bug that you find which is, let's say the function is not working at -40 or 120? So do you find that in post-silicon analysis? And is there any way that we can emulate that scenario in pre-silicon?
Yeah, that's a good question. I mean, the kind of issues as you talked about the temperature, right? Actually, it's very important that your chip has to work, let's say from -40 to 125. And there are some of the issues what we see at cold, right? For example, let's say especially the mixed signal IPs, right? For example, you have PHYs like CSI PHY, camera PHY, display PHY, or PLS, right? Or which could be some sensors, right? Because analog is very sensitive to temperature, right? And only at sea, some same chip, if I run it at room, it passes. But when I run it at -40, I see my PLL doesn't lock, right? Or let's say at mixed signal IP like PHY or something which we are designing, I start seeing a failure. Then it's very important to understand, right? To go back to the designer and understand. Of course, on post silicon, we can do a lot of debug and see where exactly it's failing. But once you have that information, it's important to go and check in the design. For example, in the mixed signal IP, right? They do run a lot of spice simulation, right? Circuit simulation. Again, that is the area there you need to see, right? Hey, certain things, let's say if my IP was working at room but failing at cold, do I have a marginality in circuitry which get exposed when I run it at cold temperature? So those kind of issues again we find, which are mostly the MSIP circuit defects I will call. That is one category, and of course, there could be some timing issues also, right? For example, certain timing issues which you can expose only at hot temperature, right? For that, again, you have to go back to the STA and see, hey, whether in STA have you closed all the corners or those things, right? So that way, I mean, every issue which you find that in your volume temperature testing, it's important to go back and understand in the pre-silicon, right? What we could have done better to catch those issues in pre-silicon. So that way we can clearly debug and root cause, right? And improve our methodology. This is something if I had done in pre-silicon, I wouldn't have seen that issue in the post-silicon, right? So those kind of issues we do find in the post-silicon. Any other questions? Yeah. Yeah, that's a good question. I think in my talk, in my speech, I spoke about the software content, right? But let's say when you run actual software test mission mode, it's very hard to debug. Let's say something fails, right? I start seeing a hang or something. So it is very important if you want to debug where exactly that failure has happened, you have to have a test which is independent of OS or the actual software stack, right? And which is something which is easier to code and debug also. So that is what we call as the bare metal test content, right? Where you don't have a complete software stack, you don't need Android or you don't need a Windows platform, but with the bare metal drivers and then the test, right? Like DV test, we should be able to reproduce that issue and debug, because debugging in the actual software environment is very difficult. Something with a simpler test, if we can reproduce, right? That is what we call as the bare metal content. Yeah, again for that we have to develop all the test scenarios, right? Again, some of the this thing, right? The drivers and all. Sometimes wherever possible we use from DV, and again if it is not possible, then we develop our own drivers. But for that, again, we need to have a comprehensive framework, right? Where I can do a standalone test, I can do a concurrency test without having too much of overhead or complexity, right? In terms of the test content and this thing, which is something easier to debug, right? So again, the methodology is very similar, where you start looking at the architecture spec, design delta, and based on that, you plan your validation test content, right? And something which you can develop on your own, and which is independent of OS, independent of software, and something which you can debug faster. Okay, this is pretty much okay. Thank you very much.
Sure, sure.
So, as a token of gratitude from IEEE CAS Bangalore chapter, I now invite Prabhavati ma'am to hand over the token to sir. So just because we're running a little behind schedule, we're going to be pushing the tea break to the end of the day's proceedings. And we'll move on with our next technical talk for the day. So our next technical talk is by Dr. Srinivas Pinishetty, Assistant Professor in the School of Electrical Sciences at IIT Bhubaneswar. A little bit about him. Srinivas Pinishetty received a PhD degree in computer science in January 2015 at INRIA University of Rennes in France. After completing masters in computer science at Eindhoven University Technology in 2009, he continued as a PD engineering trainee at TUE for 2 years. As his master's thesis project, he worked at ASML Veldhoven, Netherlands in 2009 and as a software design engineering trainee at OCE Technologies in Venlo, Netherlands in 2011. He is an assistant professor in the School of Electrical Sciences at IIT Bhubaneswar. Prior to joining IIT Bhubaneswar, he has worked as a postdoc researcher at the University of Aalto, Finland, and later at the University of Gothenburg in Sweden. His research interests include formal methods and software engineering in general, with emphasis on runtime verification and enforcement in particular. I'll hand over the dais to Srinivasa.
Okay, yeah. Hello all. So I think it's one hard thing is to give the talk at the end, towards the end, right? So I hope that I'll be, able to keep you interested with some things that I'll be talking about. And yeah, so let's try to keep it more interactive. I think we don't need to finish everything. Of course, I think we'll be spending about 40-45 minutes. So let us make it more interactive. Feel free to interrupt. Okay. So yeah, so I think most of the other speakers mentioned about various formal verification approaches, right? So if we look into formal verification techniques, so I think everybody, like most of you must be familiar with various static formal verification techniques like model checking and then theorem proving, right? Everybody must be using various static formal verification techniques. And so formal verification techniques also come under, there are also dynamic formal verification techniques. Of course, there are also formal approaches techniques used for generating test cases automatically, right? So there are toolings approaches used on how to automatically generate test cases that provide certain notion of coverage, right? And what I'll be talking about today is more about another dynamic formal verification technique, which is called as runtime verification, and runtime enforcement is an extension of runtime verification techniques, right? So I'll very briefly introduce to you about what these techniques are. So by the way, so what we mainly focus on, my team, my students, along with my students, so we mainly focus on working on the theories, the algorithms and techniques building the tools and the algorithms, right? I think some of them have already talked about, for example, the model checking technique, right? So when we want to apply the model checking technique, so for real, systems, can we directly use the actual system? We cannot really use the actual system for applying model checking, right? We need to, as most of them have already told, we need to first build an abstract model of the system, right? And also the requirements, of course, we need to first, formalize the requirements, right? Put them in some formal logic, right? Formal temporal logic or other formalisms, right? Then those are given as input to the model checking tools or the approaches, where the model checker takes care of whether the abstract model satisfies the given specification or not, right? So one example of various things, of course, like we need to work on the model checking algorithms and techniques, but then also we also need to focus on like one particular example, like building the abstraction, right? From the real system to the abstraction. So that is not also an easy problem, right? Because we don't want to build the abstractions by hand, right? We need formal ways of building the abstractions, right? So one example problem like some of our students, some of my students are currently working on is, for example, if I have like a sort of a neural network which is there in the system, right? How do I build an abstract model of that particular neural network, right? So that I could I could formally verify properties over that, right? So it's not an easy problem of coming up with an abstraction, where we also need to show that the abstraction is, so if I prove something over the abstraction, it will also hold on the actual system, right? Otherwise, what we are proving is useless, right? So we need to come with sound formal techniques on how to build the abstractions, right? So that is one particular area that we focus on. We build the algorithms and techniques, right? So the other, area that we mainly focus on working is on the dynamic formal verification techniques, which come under the runtime verification enforcement schemes, right? So we build the algorithms and tools for runtime verification and runtime enforcement. That I will very briefly introduce to you about today in the next 40 minutes, right? So I will give a very brief introduction about what runtime verification, runtime enforcement means. And so I'll talk about like what approach we use for how we obtain enforcement monitors for real-time properties, right? And later on I'll deal with how we what approach schemes we use for coming up with these enforcement monitors that are basically suitable for reactive systems, right? How we can apply these techniques for reactive systems. Then we'll see very briefly about some applications that we are working on. As I said, our main focus is on coming up with these algorithms, techniques, and the corresponding toolings, right? But then we also focused on applying these things in particular domains. So I'll very briefly mention on some of the applications. And of course, finally, we have some thoughts maybe for discussion, because some of the, so we have different experts from industry. So we also want to see how the toolings approaches we build are suitable in this particular context, right, in this domain. So we could have some open discussion towards the end if time permits. And finally, we'll summarize, right? So yeah, so I think you must have understood like from the previous talks that what is one of the difficulties with the formal static verification techniques like model checking, for example. When we want to apply like model checking, what are the challenges we face for example, also in the chip verification, context. So one of the challenges, like as the complexity of the system grows, right? To come up with an abstract model of the system is really a challenge, right? How do we come up with a real abstract model of the system that is sound and how that can be used for the verification purpose, right? Let us say with several efforts, we come up with an actual model of the system, right? That we could use for verification. But then we have several properties to be verified. So scalability of these verification algorithms is also another challenge that researchers are trying to address them, right? So what I basically will be talking about this runtime enforcement verification techniques. Of course, I'm not saying that, okay, now that this is an alternative to the static verification techniques. No, of course, we should use everything in combination, right? We should be verifying whatever is possible statically and whatever. So do you all also agree with me with this point that, okay, let us say I do thorough verification, right? I do thorough verification at different stages. Now my system is like deployed, it is in use. Is it the case that the system will work, bug-free forever? Let us say I do like all the efforts of, formally modeling the system, I will thoroughly verify the entire spec, right? So is there any guarantee that the system is never going to fail? Still, there is no guarantee because of the security issues, right? can we consider all the security issues during design time and verification time? No, because there are new security concerns that may pop in, right? So we never know, right? So what is actually proposed, the formal runtime verification enforcement schemes, is basically that, okay, now there is a system that's already deployed, right? Now when we take into account any safety critical system, for example, when the system is actually executing, we basically want to check how the system is doing with respect to not the entire specification, but with respect to the critical safety aspects, critical security aspects. We definitely need to monitor those when the system is actually executing, right? To prevent something bad from happening, we definitely have to monitor the safety, the critical safety security aspects, right? So what these approaches basically, if we take an example of a runtime verification scheme, the approach basically focuses, here the focus is on not all behaviors of the system. The verification monitor focuses on what the system is presently doing. We are focusing on the current execution of the system, right? So it avoids the problem of modeling the system formally. I don't have to, I can consider the system to be a black box. I can apply this to black box systems, right? What I all need is the current behavior of the system, right? So given a formal, requirement or a formal property to be verified, which is denoted as phi here. So the aim of this formal monitoring techniques is to generate or synthesize monitors from the formal specifications, where the monitors could be integrated with the systems, and the monitors can check the critical properties during execution of the system, right? So since we don't require any formal model of the system, we don't have the scalability issues here, right? So if we take the example of a verification monitor, right? So what it basically does is, the input to a verification monitor is a stream of events, right? It's like what the system is doing during execution, right? And what it basically outputs is a stream of verdicts that gives us information about whether what the system is doing satisfies the properties that we want to verify or not, right? It basically takes a stream of events and emits a stream of verdicts, right? So when we look into real critical systems, right? So now when something bad is about to happen, can we do better, right? Instead of just observing what the system is doing and saying, okay, this property is violated at this point, can we do something better? For example, can I prevent violation from happening, right? So that is the focus of these runtime enforcement monitoring schemes, right? So when we take the example of an enforcement monitor, so at an abstract level, we can consider these enforcement monitors like filters, right? Like filters or an additional layer that is added on top of the system, right? So an enforcement monitor or an enforcer also takes a stream of events as input, but what it emits as output is a stream of events that actually satisfies the properties that we are monitoring, right? That we want to check at runtime, right? So for example, if something bad is about to happen, the enforcer has the power to suppress that action from happening, right? For example, if we take the example of an autonomous vehicle, right? So when there is an obstacle, of course, the braking should come from the controller, right? If the controller is not sending a braking command, the enforcer has the power to insert, for example, send a braking command, right? So we want to prevent something bad from happening, right? So monitor the execution of the system, prevent the critical violations from happening during runtime, right? So what we mainly, I'll first very briefly talk about, runtime, verification approaches. So when we look into the runtime, so when we consider the formal, aspects of this runtime verification and enforcement, the focus of all these formal techniques is about given properties in some high level formalism, right? As designers, as design engineers, what you basically do is you want to specify what are the critical properties, right? What you want to monitor during runtime, right? So you basically specify those things, and now you want to automatically get the monitors, right? So what we mainly work on is how the monitors can be generated automatically once a designer gives the properties, right? So there are, regarding verification monitoring, of course, there are various approaches proposed on how to automatically get the verification monitors from properties expressed in various formalisms like temporal logic, automata-based formalisms, right? There are various approaches for untimed, properties with real-time constraints, right? There are different techniques that are, there in literature, and the toolings are also available, right? If we see a bit more about the context of a verification monitor, as I have been saying, So what the approach basically gives us is, given, let us say a designer specifies what are the critical safety security properties, right? I'll denote it as P here, right? So the approach automatically synthesizes a verification monitor. So it generates a verification monitor. Now I don't need to worry about correctness of this verification monitor. This is also a piece of component that is built, right? Now I don't need to worry about the correctness of this verification monitor because the approach basically proves that the algorithm is sound, right? Meaning if the approach is used for generating monitors, then I don't need to verify the monitor itself because it is sound by construction. It is correct by construction, right? So what is the need of using these formal techniques for synthesizing these components? I don't again want to, so these, somebody might ask me that, okay, now why are these formal techniques, right? I can implement a component that does this monitoring task. Of course, we can implement by hand, but what is the guarantee that these components are correct? There is no guarantee, right? So that is the reason we work on this formal techniques where we take in the specification and we automatically generate components that work as these monitors. And once our techniques are used, the monitor components is supposed to be correct by construction. So we don't have to again verify the monitor component itself, right? So if we take the example of a verification monitor, of course, once a designer gives the properties, the approach synthesizes these verification monitors, where the monitor can actually observe a system being that is currently executing, right? The event emitter could be the system that I want to monitor, right? So where the event emitter does different things, it does different actions, which are observed by the monitor, and the monitor basically says currently, of course, the properties are okay, or at some point if the properties is violated, the monitor gives in a signal saying, now the property, the safety thing that you're monitoring is about to be violated, right? Or is actually violated, right? So let us skip these formal notions. Of course, like here, there are different verdicts, some like true and false, they're basically called as conclusive verdicts, meaning once I emit a verdict that is true, right? Of course, observations, they keep on evolving over time, right? So at initially I might observe nothing, but then after 10 time units, I might observe some set of events, right? After 20 time units, I might receive more events. Observation keeps on evolving with time, right? So depending on what is currently observed, if I say that, okay, the verdict is true, meaning the property is satisfied. So true and false are like conclusive verdicts, meaning if I am saying from my current observation, the property is satisfied, the property is true, it means that whatever may come in the future, the verdict is not going to change, right? Once I give a conclusive verdict, the decision should not be changing, right? And currently true and currently false, they are sort of inconclusive verdicts. So I can't really say about the future, but currently the property is satisfied. I don't know in future it may be violated, right? So these are called as inconclusive verdicts, right? So the monitor that is generated should satisfy various formal constraints like impartiality and anticipation. These are basically what I'm talking about, right? Meaning once I am able to give a conclusive verdict, conclusive true, then the monitor should give a conclusive verdict as soon as possible, right? If it is able to say, okay, with my current observation, I'm going to say the property is satisfied, then it should be saying that instead of saying currently true, right? It should be giving a conclusive verdict as soon as possible. What is the benefit of giving a conclusive verdict as soon as possible? Is there any benefit of giving a conclusive verdict as soon as possible? Conclusive true or conclusive false? And also like so that is one thing that can be done, right? We could think of a defensive measure. The other aspect is I could turn off the monitor, right? For example, when do I need to keep on continuously running the monitor? If the monitor is not able to say anything conclusive, right? It's only able to say about what the current observation is satisfying or not satisfying, but it's not able to say whether any future continuation also will be satisfying or violating, right? So if I'm able to give a conclusive verdict, then what could be done? I could actually turn off the monitor, right? Because when is a conclusive true verdict given? A conclusive true verdict is given only when every future, let us say I observed some trace which is sigma, right? Only if all continuations of sigma will also satisfy the property, only then conclusive true is given, right? So when I'm able to say that, okay, now I observed sigma based on observation of sigma, whatever sigma extends with will also satisfy the property. If I'm able to decide that, then do I need to wait for more events? No, right? Because the verdict is not going to change. Once conclusive verdict is given, I know it will remain true forever, right? Irrespective, whatever may be received in the future, I know it will remain true, right? So I will discuss very briefly about runtime enforcement, monitoring in the context of real-time properties, right? Because most of our major works also lie in this area. I'll very briefly mention about what this area is about, right? So when we looked at a verification monitoring mechanism, right? So what the verification monitor is fed as input? The current observation of the system, right? Which is basically information about what the system is doing over time, right? And what it is emitting as output, a verification monitor is emitting a stream of verdicts, right? Whether currently properties are holding or not holding, right? So when we take the context of an enforcement monitor, so it also takes a stream of events as input, but what it emits as output is a stream of events that must satisfy the properties being monitored, okay? So it is basically, you can consider this, enforcement monitors as a sort of a wrapper, safety wrappers on top of the system, right? We want to build safety wrappers on top of the system, right? Which safeguards the system against some critical aspects, right? So those kind of components can be generated automatically using the approaches that we have, right? So what are the characteristics that an enforcement monitor should fulfill? One key characteristic is that whatever is emitted as output by the enforcement monitor should always satisfy the property being monitored. So it can never emit something as output which will be violating the property being monitored, right? So in a sense, it guarantees that the properties being monitored will never be violated at all, right? So in order to so in a sense, you can understand like this is basically like, a sort of a component that transforms the input sequence to an output sequence, right? Where the output sequence will be satisfying the property that we want to satisfy, right? Property that we want to monitor. So there are different like enforcement mechanisms proposed. So some of the enforcement mechanisms are sort of equipped with memorization mechanism, right? So for example, it's not good to like alter the system behavior completely, right? So the enforcer should be having limited capabilities with respect to what it could do to the actual event that it observed, right? So some basic, enforcement monitoring mechanisms are basically equipped with the memorization mechanism, which basically what kind of operations these approaches allow. They basically read events. Of course, if currently the property being monitored is not satisfied, they memorize those events in their memory, right? They remember those events in the memory. And after observing more events in the future, when it notices that the properties could be, the property being monitored is satisfied with the events in the memory along with the new event received, right? So then it can, release those events to the output, right? So what is the power of the enforcement mechanism? Of course, some frameworks support, memorizing, delaying events by memorizing those events in the memory and releasing them later on, right? So memorizing or suppressing events. So there are some frameworks that allow to suppress, discard some illegal events, right? And there are some events that allow to instantaneously edit events, right? So we'll discuss about those briefly. So I think needless to say, like also in the context, in the domain of this SOC chip verifications, of course, we have several properties where timing is important, right? So for example, what are these timed, properties? Here I'm not only interested about the sequence in which the actions are happening. It's not about after an A action B should happen, right? I'm also interested in how much time is elapsing between these two actions, right? After a read request, the request should be processed within so and so delay, right? It cannot be like unbounded delay, right? So whenever we have this timing into account, they're basically called as timing properties, right? It's not only about the sequence of events, there are also constraints on when the event should happen or how much time can pass between different events, right? So they're basically called as, timed systems, right? So in typical any real applications that we work on, we basically encounter properties with timing constraints, right? Think of any real-time embedded system or also these related to hardware systems, right? We have several properties where timing is important, right? So there are like several works on how to automatically generate enforcement monitors for untimed specifications, but nothing was existing for real-time properties, right? Properties with timing constraints. So our works, I think during my PhD time, like some of our key works focused on how to generate enforcement monitors for properties with real-time constraints, right? So if we see in abstract about the technique, right? The approach basically is that, okay, what is given to the approach? So the property, the time property to be monitored and enforced is given as input to the mechanism, right? So what we want to actually, synthesize or generate, given the property, time property, we want to automatically generate an enforcement mechanism, right? So where the enforcer sits between an event emitter, which is like the system being monitored, and the event receiver, where the event receiver could be another system or the environment, for example, right? So what we want to do is to automatically, synthesize these monitors, right? So there are different, problems. Now here we want to devise algorithms, techniques, which will work about how to automatically synthesize these monitors, right, from properties, right? So when we are looking into such research problems, of course, we need to keep some constraints, right, initially. What are the different constraints, right? So one problem is, what are the properties that we actually consider? Do I consider all kind of time properties to solve this problem? And do I consider in what formalism the properties will I be taking as input? So there are various formalisms, right? For expressing timing properties, there are various formalisms, like if we talk about temporal logic, so there are like signal temporal logics like MITL. There are several time logics, right? Timed LTL, TLTL, for example, right? Or if we talk about automata-based formalisms, there is a variant of, how many of you are familiar with automata? The general automata. I think most of you must have studied about the general automata in your, I'm talking about the students. Of course, all the experts here, I think they must be familiar. So what is timed automata? Timed automata is an extension of the standard automata, where there is a provision to make use of clocks, right? So what are the clocks useful for? The clocks are useful to model the timing constraints, right? So here I'm not interested only in the sequence in which the actions are happening. I'm also interested in the timing between how much time is elapsing between actions, right? How could I basically do that? By making use of clocks, right? So one aspect is about what formalism I consider, what properties do I consider to solve this monitor generation problem. The other aspect is, what are the operations that I allow the monitor to do, right? In order to enforce the given property, what are the operations that I actually allow the monitor to do, right? Do I allow the monitor to, replace an event, to delete an event, or do I allow the monitor to only delay events and then release them later on? Do I allow the monitor to change the order of the events, that the order in which they are received? Can I change the order, right? So what is the enforcement operation that I want to allow, right, in order to satisfy, like in order to build the algorithm or technique that I want to solve, right? And of course, the implementability, right? Of course, we don't just want the abstract algorithms, we want to also realize tools from the algorithms, right? How implementable the techniques are, right? So, yeah, so when we want to solve this problem for, real-time systems, of course, the input and output to our enforcement monitor are timed events, right? What is a timed event? It's basically an action along with the timestamp, right? What does the timestamp indicate? The timestamp indicates when the action has actually happened, right? So the input and output to the mechanism are basically stream of timed events, right? Where you have an action and the timestamp at which the action has happened, right? So where the timestamps of the actions, they keep on only increasing, right? A later action cannot happen at a time before, right? At an earlier time, right? So the input and output of the mechanism are, stream of timed events, right? And the other question of how the property, what is the property specification formalism that we actually consider? Of course, we worked on enforcement monitor generation for all the regular time properties that can be specified as a timed automata. So timed automata is a very popular model that is used for verification of real-time systems, right? Formal verification of real-time systems. So it is introduced by Rajiv Allur and other researchers. There are popular, model checking tools based on timed automata, right? So also in this work, we consider like properties being specified by the designer as timed automata, right? So let us take an example. Let us try to understand like what timed automata is very briefly with this example. So here, I think everybody is familiar with normal standard automata, right? Which has locations and transitions over from one location to another over actions, right? So when we consider a timed automata, in addition to actions, we are making use of clocks, right? So what does this property actually, the automaton here actually, specifies? So here, if you see here, right? So we are basically saying that requests and grants should alternate in that order. So whenever there is a request, so here, what is an accepting state? The locations in green are accepting locations, right? And the locations in red, they are non-accepting, right? So whenever a request is happening, I am moving to this location L1, and here I am making use of a clock, right? So X is one clock that I am using to express this property, right? So whenever there is a request that is observed, I am moving to L1, and at the same time I am resetting the clock, right? The clock is set to 0, right? So the clock should start ticking from 0 from that point, right? So when the grant is supposed to happen, right? When I'm in location L1, and when the grant is actually happening, what is the timing constraint that I want to check? How much time should elapse between request and grant? So there should be a time gap of between 15 to 20 time units, right? So I'm resetting the clock when a request is observed. And then when there is a grant that is happening, I'm basically checking whether the time that the value of this clock X is actually between 15 to 20 time units, right? Then I'm moving back to an accepting state. If the time that has elapsed is less than 15 or greater than 20, then I'm actually going to this non-accepting location, which is L2, right? So using this timed automata, we can express various properties with real-time constraints, right? So yeah, so the property specification formalism, of course, what we considered are timed automata. So we propose a mechanism that generates enforcers for any property that is specified as a timed automata, right? And next question was about the power of the enforcement mechanism, right? What do we allow the enforcer to actually do in order to correct the input sequence? So in the framework that we actually developed, so we allow the enforcement mechanism to buffer events. We assume that the enforcer is equipped with some memorization mechanism, right? It can store some events for some time. So the enforcer, if the input events are not satisfying the property, the enforcer could store the input events in its memory, right? And it could release them at a later point when it observes more events that will allow satisfaction of the property, right? So it is allowed to, the enforcement operations are only delaying and suppressing. So when there is some event that is received, where upon receiving that event, the violation cannot be avoided, right? It is actually leading to some kind of a state where the violation cannot be avoided, right? Which is called as a dead state, right? Then is there any use to keep that event in the buffer? There is no use, right? Because whatever might come in the future, I'm not going to satisfy the property at all, right? So the mechanism gets rid of those events by suppressing such events immediately, right? So delaying and suppressing is what the enforcer is allowed to do, right? So if we just so I think due to time, let me skip the examples. I think you got the general idea, right? What the enforcer is supposed to do, right? So let me skip the example. I think we are running short of time. So what we basically do in summary is, of course, like here I'm not I'm just giving you some idea of what the mechanism that we build does, right? So we are not going into the internals of the algorithm on how we build the enforcer and what approach we use to show that the enforcer is sound, it is correct, right? So what the enforcement mechanism does is basically discussed briefly, and the approach that we follow to actually generate the enforcers is the following, right? So we first need to decide on what are the requirements or the constraints that the enforcer should actually fulfill, right? So there are various constraints or requirements that we want the enforcement mechanism to fulfill, right? So one is basically called as soundness. What does soundness basically mean? As we have been discussing, at any point in time, whatever is released as output should be satisfying the property. It can never, the output of the enforcer can never violate the property, right? If we discuss about the other constraint, for example, transparency, right? So is it essential for the enforcer to perform any corrective action if the actual input is correct? If the actual input is satisfying the property, should the enforcer do something to that? Should the enforcer do something if the actual input is no, it should not do anything, right? So whatever is good, the enforcer should leave it as it is, right? So the actual behavior should be should be altered as minimally as possible. It shouldn't interfere unnecessarily to the actual behavior of the system, right? So that is basically called as transparency, right? So first we decide on what are the constraints or the characteristics that should be fulfilled by the mechanism, right? Then we define the mechanism at the abstract level as functions. This is basically like a function, right? At an abstract level, it takes a stream of events, should emit a stream of events. So we can visualize this at an abstract level as a function, right? So then we define the enforcement mechanism at an abstract level as a function. Then we also discuss the operational, the semantics of the enforcer. So let us not go into the details. So finally, like, what is the takeaway from here? Of course, like, we basically come up with algorithms and toolings that are also implemented, which are correct by construction. So once you use our algorithms and toolings to get these enforcers, you don't need to verify or test the enforcers itself because they are proven to be correct, right, using the technique, right? So there are also tools available, as I said, right? So from the theory that we built from the proofs, we also implemented the techniques as tools, which are open source. So you can, if anybody is interested to use the toolings, you please contact me. I think they are open source and you can utilize them, right? So yeah, so what you need to do as an engineer, as a designer, you only need to think about what properties you want to enforce or verify. You formulate them in the required, property specification formalism. You give them as input to the tooling. The tooling will give you the corresponding, monitor, right? Verification or enforcement monitor, right? So the theory behind the tooling, of course, you don't need to worry much about it, given you know what it actually does, right? So of course, there are later on like various, extensions to this. Of course, like when we wanted to apply this to real, practical scenarios, we also came across like scenarios where we need to take into account events, where the events also carry some data, for example, right? Events cannot be just like, simple events. We may want the events to carry some data along with, right? So we extended like the property specification formalism. We have introduced something called as parametric, timed automata, where the events are made parametric, and internally some variables could be used to, like variables like counters could be used, right, to keep track of how many times some event has happened, right? For example, if I want to keep track of how many times a request is occurring, right? So I could do that with a simple internal variable, right? So this is only for ease of, modeling more complex properties. When we talk about real systems, we have more and more complex properties, right? Now, if we use the standard timed automata for modeling real complex properties, the properties again will get larger, right? Will get complex. So will get cumbersome. So in order to ease property specification for complex properties, we have extended timed automata with different, aspects, right? And we have like the corresponding monitor generation techniques for this extended version of timed automata. So in summary about this topic on enforcement for real-time properties, so we have a mechanism that generates these enforcers by taking input. As the designers, you need to provide the properties that you want to monitor as input to the mechanism, and you will automatically get the enforcer that is generated that you can directly utilize, right? So yeah, there are toolings that are implemented. They are open source. You can make use of them, right? So there are like few other related, works. For example, we may not be in typically like, okay, this is also coming from one particular practical scenario, right? When we were discussing about application of this in some practical scenarios, then some of the experts from that side said that, okay, no, So it may not be really practical to assume that the enforcer has control over all actions, right? Some actions, the enforcer some actions are like real critical actions, which they don't want the enforcer to take control over, right? So we have later on worked on enforcement with partial control, where some actions are categorized as critical actions, where the enforcer can only observe that happening, but it cannot really take control over those actions, right? And what did I say in the beginning of this session? How many of you are following? Of course, I know that, okay, the last session is always difficult, right? What did I say at the beginning of the session? What did I say about the system being monitored, that is the event emitter? So does the monitoring approach need knowledge about the system being monitored? So if I want to use utilize these monitoring approaches, is it necessary to give a model of the system? The system could be a black box, right? That is one beauty advantage of these techniques. I don't really need to know the internals of the system. If I know the interface, I'm good, right? I can observe what the system is doing at runtime. So few of the other works that we did later on. Let us say, suppose that I have some knowledge of the system. I don't really need any knowledge of the system. The system being monitored could be a black box. But suppose I have some knowledge about the system. So if I provide that as input to the enforcer generation mechanism, can the enforcer generation mechanism do something better? Right? For example, instead of delaying event, keeping it in its buffer, can it release some event earlier, knowing, okay, as per the system knowledge, it's definitely going to produce something in the future. If the enforcer knows that information, it could do something better, right? So this we basically call as predictive enforcement mechanism. Of course, it's not necessary that the enforcer is given knowledge about the system. The system could be a black box, but in case we have a model of the system, the enforcement mechanism could actually benefit from it, right? So we have a proposal mechanism for that. And so we are also still working on a lot of things. For example, like one of the aspect is about scalability, right? I think different experts have spoken about scalability. So what is one way to deal with scalability issues? For example, forget about the monitoring runtime techniques. Think of static verification. Let us say you have really worked hard for several months to build a model of the system. Now you have also written down, you have invested a lot of time to formalize the properties. But once you give it both as input to the tooling will time out, it will not give you any result. So are you going to leave it there, or how are you going to tackle the problem? So one aspect is to make it more abstract, right? By cutting down some more unnecessary things, right? So the other way is sort of do things in a compositional way, right? So now, of course, for example, I have taken the overall whole picture. So now the system is not, the verification algorithm is not scaling because the state space has exploded, right? Now, how do you basically approach the problem? Now, I look at how can I break the overall system into subsystems. Now, I am not going to talk about the overall system, I break it into subsystems, right? I verify the property over each subsystem. Now, I somehow have to argue about verifying this property over each subsystem, also boils down to verifying the correctness of the overall system, right? So we basically do things in a compositional way, right, when there are scalability issues, right? So also with respect to enforcement, compositionality is a very important aspect, right? Now, when we want to apply this verification or runtime enforcement or verification techniques, is it the case that, okay, we only have one critical property to be checked at runtime dynamically, or do we have several properties? So we usually have several properties, right? There may be several, safety related, security related aspects that we want to verify, right? So what is one way of generating a monitor for several properties? So one simple way is build a product, right? Combine all the properties, get one larger, bigger property. You build one monitor using the approach for one larger, bigger property. What are the drawbacks with it? So the drawbacks with it is, again, so this is an approach that should work at runtime, right? Yes, that is supposed to work along with the system at runtime, right? So one drawback with that is, of course, like the efficiency of as the complexity, as the number of properties grows, the overall time it takes to do the enforcement operation or to give the verdicts, it increases with increase in the number of properties, right? So how to counter this problem? Of course, we may look at doing this compositionally, right? When we have several properties to be enforced or verified, I look at generating monitors for each of them individually, right? And then we look at schemes on how to combine the outcomes of these, right? So for example, putting these enforcers one after another, or running these enforcers or monitor components all together in parallel, right? The compositional schemes also play a role with monitoring, right? So we have been looking into like investigating on these compositional schemes as well, right? There are also frameworks where we do the monitoring in a compositional way. So what is one of the other necessities for compositional monitoring? When we talk about in the context of security of chip verification, when we talk about SOCs, verification of SOCs, right? Let us say I use this dynamic monitoring components for verification of SOCs. So can you tell like why do we actually need compositional schemes? Why do we benefit from doing things in a compositional way? Where do we benefit from? Sorry, yeah. Integrating different components together. So when we talk about security aspects, right? So of course I don't have all the security related issues in one go, right? Let us say I have some n number of safety security issues. I have built a monitor, right? The monitor is deployed. Now later on somebody comes and says, okay, now the system is prone to this new kind of attack, new kind of security vulnerability. So am I going to rebuild the entire monitor from scratch? No, if I am doing it in a monolithic way, I should rebuild the entire monitor from scratch. But if I am doing in a compositional way, I don't even need to know what properties are monitored by the current monitoring system. If I know like what is the property to be checked to counter the new security issue that is reported, I could only build one new monitor for that, and I could just put it in parallel or series with the current monitor that is executing, right? So yeah, we never know like what kind of issues we need to deal with, right? So doing this sort of monitoring in a compositional way is actually essential, right? So that is what we are also like currently looking into investigating, right? Yeah, so this is another problem. Of course, I said that mechanism supports storing events, right? The enforcer like could store events and then release later on, right? So in the traditional techniques, it is assumed that the enforcer has unbounded capacity. It could store any number of events, but that is not really practical, right? So when again we were talking with some members of applying the techniques, then they said it's not really practical to have the sort of a memory of the enforcer unbounded, right? So then we later on worked on extended the scheme of enforcer generation, where we put some constraint on the buffer, right? In addition to the property, so some constraint on the buffer size is also given as input, right? So I think we may not like go into details here. So yeah, so these are all the things that we have worked on related to monitor generation for real-time properties, right? So put the techniques that we discussed so far that allows delaying and buffering. So can it be applied to reactive systems? So cyber physical and reactive systems. So the schemes that we discussed, of course, they're not really suitable for the other class of systems, right? For example, systems that are reactive in nature, they should actually respond instantaneously, right? It's not possible like to say that, okay, now the system want to do this action. Now I will wait for some more time to see, because it's like a cyclic thing, right? It basically observes and reacts in the same cycle, right? So delaying and buffering events is not really suitable for reactive systems, right? So for reactive systems, we have proposed different class of enforcement frameworks that are really suitable for reactive and cyber physical systems, right? So I think due to time limitation, I think we'll not be looking much into this, but I think let me just talk. So by the kind of reactive systems, what I mean is systems which are sort of reactive and bidirectional in nature, right? If we take the heart pacemaker closed loop system, it's a sort of a reactive system, right? Where the pacemaker has to sense every period, every tick, the pacemaker has to sense the heart activity and it should produce the required pulses, right? Here we cannot really, delay what the system has to do, right? It has to react instantaneously, right? So we have like a different, framework for enforcement monitoring generation that is suitable for, cyber physical and reactive systems, right? Where the enforcer, sits between the environment and, and the program or the system being monitored. And it is sort of bidirectional where the enforcer like first observes inputs, it rectifies the inputs as per the property, right, which is fed as input to the program or the system, and later on observes the outputs of the system and rectifies them as needed as per the properties, right? So the overall approach is something similar. So we could actually, skip this given, the timing, right? So I'm skipping the details, but those interested, you could, those who are working on these kind of things, if you're interested in getting the toolings, knowing more about this, you could actually, get back to me, right? So yeah, here again, like for reactive systems, we have again proposed, frameworks for monitor generation where the users or the designers could specify the properties to be monitored in high-level formalisms like automata. The approach automatically synthesizes monitors that are correct by construction. So what is correct by construction? It is proven that the approach, the monitor that is generated is sound, transparent, etc., right? We have talked about various constraints, right? So I will so here are like some of the publications in this domain, right? Anybody interested, like you could get back to me, we can discuss more details, right? So I just want to mention about few of the applications, right? Of course, as I said, our group, like myself and some of my students, we all work on the theoretical parts, right? So how to like devise algorithm for so and so task and how to see that the algorithm is actually implementable as a tool, right? So we don't really focus much on the application side, but then we have been looking into recently into some applications of the frameworks that we have been developing, right? So I'll just mention very, briefly about this. So one of the, applications areas that we are currently looking into is in the context of healthcare, right? So everybody knows about implantable medical devices, like for example, one example is a pacemaker, right? So do you all know that, okay, the pacemaker like IMDs are also prone to various security issues? How many of you know that pacemakers are also prone to various, security issues? So these kind of IMDs, right, these kind of implanted devices that are actually implanted, they are also equipped with some radio wireless communication facilities. So why is it provided? It is provided because it's not really possible once, once it is actually implanted, if some parameter has to be changed by the doctor or the medical practitioner, they don't really again want to cut open and to change the things, right? There need to be some way that the doctors can communicate with the device and to set the parameter accordingly after implanting, right? So these devices, most of these devices, they're also equipped with these wireless, communication features, right? Which are like misutilized by, hackers, right? It is actually shown that various pacemakers are also prone to hacking. So where the hackers could change the parameters of the pacemaker, that will make the pacemaker to send the pace signals very rapidly. If the pace signals are sent very rapidly, what can actually happen? The person may actually die, right? If the pacing happens too rapidly, the person will die, right? So there are various instances actually reported along this, right? So what we actually proposed using this formal, monitor generation schemes, what we actually proposed is on how to non-invasively monitor the safety of an implantable medical device, for example, a pacemaker, right? Here, we don't want the monitoring solution to actually talk to the pacemaker because we want to avoid communication with the pacemaker, right? So how to actually non-invasively, without communicating with the device, how to non-invasively monitor the safety of the device, right? And the person wearing the device. So we have basically noticed that, so I think nowadays, I think everybody is having these wearables, right? The wearables are actually having these sensors that could continuously sense our ECGs, PPGs, all these things, right? So we have seen a nice correlation between the ECG, for example, and the activity of the heart pacemaker closed loop system. So for the safety of the heart pacemaker closed loop system, there are certain critical timing intervals, right? That are like very nicely captured using the peaks in the ECGs, right? Using different activities in the ECGs. So without actually communicating with the pacemaker, by actually monitoring the person physiological signals, for example, by monitoring the ECGs, different activities in the ECGs, we could actually detect whether something abnormal is happening to the pacemaker, right? So we have basically proposed a scheme for that, where in this scheme, the monitors that we generate, right, they're using from formal policies, the monitors that we generate, they're basically deployed in these schemes, right? So another example is related to autonomous vehicles, right? Now I think some of the experts also mentioned about autonomous vehicles, right? So, and nowadays there is increasing use of these AI models, right? So specifically when we take examples of these autonomous vehicles, everybody want to design components in these autonomous vehicles using neural networks and other kind of schemes, right? So one difficulty with these kind of models, right, neural networks and other AI kind of models, they are really very, very hard to verify statically, right? So what we actually proposed here, of course, this is a very small prototype system that our students actually built. So what we actually proposed here is, let us say there is a component that is actually built, right? Let us say there is a component that is built that takes care of, for example, the velocity or the steering of particular autonomous vehicles, right? They are built using different neural network, using various AI components, right? So now, what we want to basically do is, of course, if there is some obstacle that is appearing in between, so the controller should be sending the braking commands, right? So if the controller is malfunctioning, then of course, we want to prevent safety of the vehicle during runtime, right? So here what we have shown using this prototype system is, given the AI components deployed in such environments, how could we safeguard the overall system by deploying the safety enforcement wrappers, right? So let us say there is a system that is working with different AI components that takes care of the steering, acceleration, different things of the vehicle, right? Now what I want to safeguard is the minimum safety of the overall vehicle, right? What could be the minimum safety properties? If there is an obstacle within so and so distance, there should be a braking. The controller should not send accelerate. There should be a braking, right? That is one example of a safety property, right? So we have used our enforcement schemes to identify these properties. We have integrated them with the overall components, where the enforcer actually kicked in to stop to whenever the controller is sending some wrong commands, it's basically preventing that from happening, right? So I think we have built a simple prototype to illustrate the use of these enforcement schemes, right? And yeah, so with regard to the other kind of applications, right? Of course, we have been working with other collaborators from University of Auckland. So we had a lot of discussions on at what level these enforcers should be actually sitting, right? Should I deploy these enforcers at the software level, or at the OS level, or at the hardware level? So what is actually better, right? So our collaborators, they actually basically proposed that, okay, having these enforcers at the lowest level possible is indeed a better way of preventing malfunctions, for example, right? Why is it better to have these enforcers at the lowest level possible? Why not at the application level? So we are talking about various security issues, right? If the enforcer is also deployed at the application level, it may be also prone to different kind of security issues, right? So when we talk about applying this sort of enforcement schemes for industrial control systems, what is basically done is, we have taken the same theory, the same algorithms, but then we have also looked at how to synthesize enforcers, which are basically hardware enforcers. We have looked at from properties to generating the VHDL code, right, from which we could synthesize the hardware, right, where we could actually integrate the enforcers just before the actual physical plant inputs in. So from with the between the physical plant and the PLC IOs, right? Between these, the enforcers could actually be sitting, right, at the lowest level possible, right? Yeah, and as I said, recently we have been focusing a lot in the area of healthcare, applying these techniques in the area of healthcare. So I think one example I've already given is about securing the implantable medical devices, right? So we have been looking into security of pacemaker, security of insulin infusion systems. And we have been also looking into how these monitor enforcer synthesis approaches could be used to generate, components that could be used for the general health monitoring, right? So how we could combine the AI schemes together with, formal enforcement monitor generation to build, robust, health monitoring applications, right? So anybody interested in this field could also get in touch with me. So yeah, I think I didn't speak much about the applications of these schemes in the context of chip verification or the SOCs or the memory systems, right? Because I have not specifically not much worked on applying these to these kind of systems, but I'm sure that they are definitely applicable also in this context, right? The schemes that we are building, the toolings that we are building, I'm sure they're also applicable in this context. So here I just wanted to give a few pointers that I think some of you can actually look into. Maybe we can look into some of these aspects together, right? So for example, I think as I said, right, what we focus on is on building the the techniques, building the theory, and building developing the algorithms and the toolings, right? We mainly focus on the theoretical parts, right? But then when we look at the real applications of these things, we come across several questions, right? So one of the questions that we come across, as I said, is from the context of security of the monitor itself, where is it better to deploy? So of course, the scheme that we work on, like from properties to monitor generation, I could generate a monitor that is a Python code or a Java code, or my target could be also VHDL, as I said, right? We have these different targets. We have different monitor generation frameworks where we generate different targets. We generate Python code, we also generate VHDL, right? So I could also apply this monitor at the application level. I could also apply the monitor at the hardware level, right? So, but where is it actually better from the security point of view, right? So maybe the lowest level might have less security vulnerabilities, for example, right? And these monitors are supposed to be executed at runtime, right? So they basically observe what the system is doing at runtime. So they are supposed to be working together with the system, right? So it is expected that these monitors should not induce much overhead. So if they induce much overhead, then they are not much useful, right? So what is other direction in which the researchers are also actually focusing from the practical applications of these schemes is how to reduce the overhead of the monitors, right? So one way is, for example, to do some additional pre-processing. So let us say there are a set of properties. How could I simplify the properties, right? So there could be additional pre-processing phase, right? Or one of the schemes that is also being looked at is to make the monitor sort of time triggered, right? Instead of event by event, I may take into account a buffer of events. I may wait for a window of time. I may trigger the monitor after a particular window of time, right? So instead of every time instant kicking the monitor works periodical, right? So these are also some approaches that are being looked at. So other works that are also being considered is for the execution of the monitor, can the GPU be utilized? Right? Can I basically utilize the GPU to make not to have much impact on the actual behavior of the system? Can I run the monitors using the GPU? Right? That is also one problem to be looked at. And could we also have a separate dedicated co-processor sort of, right? So we don't know, right? So there is different things that we can look at when we talk about applicability of these schemes, right? And yeah, so also when we talk about building real systems, right? So when we talk about building real systems, as do we build each and every component? For example, building a new SOC, right? Do we build each and every component from scratch, verify each and every component from scratch? Is it done that way? No, right? So we basically take the components off the shelf, we try to fit in them to see to design our overall system, right? So what are the various challenges when we take in components off the shelf, right? When we're taking commercial components off the shelf and we are building our overall, system, our overall chip, our overall system, one difficulty to verify the overall your system is I may not have the real complete spec, right? Maybe the designer of that particular component due to certain, competitive, this thing, the overall complete spec may not be available at all, for example, right? Or the other difficulty is like, okay, checking the complete, spec when I take the components from off the shelf is really a challenging problem, right? Due to different aspects, right? So in such cases, of course, like the monitors, like, deploying this kind of monitor components might actually help, right? Where I may not be interested in the overall specification of each and every component, right? I'm interested in how I basically want to use the component in my overall system. Remember, I think I am not interested in the overall specification of some component. The component that I'm using, does it fit my need in the way I want to use it, right? The component may do several things, but in my system that I'm designing, I want the component that I picked in to do something, right? Is it actually fulfilling the need in which I'm for which I'm using it in my overall system that I'm designing, right? So for that purpose, I think like one way to deal with this is to actually use the formal monitoring schemes to synthesize monitors, where we could have these monitors like also integrated with the overall system, right? Where the monitor observes like from the peripheral bus, the monitor could observe what things are going on, right? And it could check for the aspects that I actually need from the component, right? It need not be the overall specification of the component, but in what way I want to use the component. Is it actually fulfilling that or not, right? I might actually check that at runtime using monitors, right? And yeah, we have been recently looking into verification of memory systems, right? But what we did is not in the context of using monitoring, but we have been doing this in the context of model checking, right? Where we were modeling, for example, DRAM controllers, checking whether the DRAM controller fulfills certain desired properties or not, right? But at the same time, we could also apply like the monitoring schemes that we have discussed about, right? For example, we could actually use monitors to detect row hammer attacks, right? I think everybody must be familiar with row hammer attacks, right? To identify some of such, some vulnerabilities, the monitors could actually be deployed. And when so I think we all know how these memory systems are organized, right? There are different rows. I think as the expert said, we have like sort of a grid matrix sort of a thing, right? Where there are multiple rows, right? So what is basically a row hammer attack? So when some, row is accessed, continuously simultaneously, right? So then the row is basically activated, multiple times, right? So what effect it might have on the adjoining cells when a row is activated continuously several times? It might actually flip the bit in the adjoining cells, right? And a bit flip might actually cause something abnormal, right? It might actually, so the bit that is flipped, it may be related to privilege, right? The privilege escalation can happen, right? So we could use this kind of monitors to detect row hammer attacks, for example, during runtime, right? So such kind of monitoring approaches could be used, for example. And let me not go into more details. I think the processor in memory systems, these are also gaining more attention, right? So also here, we could see how monitoring components could help, right? To verify things dynamically, right? And also I think the memory systems. So I think we have looked at, in our group, we have looked at modeling these kind of memory systems and verifying, properties. But then we have not looked at applying monitoring schemes, but we could also apply monitoring schemes for verifying properties of these memory systems, right? Like NAND flash. So yeah, in summary, I think I very briefly introduced to you about like what these formal runtime monitoring schemes are. I think I focused more on synthesis of enforcement monitors. I think I didn't go into details into the algorithms. I think I mentioned to you about what these monitoring schemes are and how you could utilize them, right? So if we talk about in general, of course, there are different, monitoring, monitor synthesis frameworks, formal frameworks, where the properties supported could be timed, untimed, as I said, right? And the monitor itself is basically unidirectional or bidirectional. We also have frameworks where the monitor is bidirectional, right? And with respect to enforcement mechanism, of course, there are various frameworks, as I said. So depending on what the enforcer actually allows to do in order to correct the execution, right? just delaying and buffering, or also allowing suppression, or instantaneously rectifying the malfunction, right, which supports instantaneous edit. And with regard to application domains, I think so far we have been looking into the healthcare domain and of course cyber physical systems. And I also mentioned about compositional schemes for monitoring, right? And of course, like the event emitter, the system being monitored could be a black box, but as I said, like we could also, if some knowledge of the system is available, we could provide it to the monitoring schemes, right? And where it could be deployed, of course, that is also a problem to solve, right? Either at the software level, OS level, or the hardware level. As I said, we have tools that generates Python code. We have like monitors. So the algorithms are the same, right? Once we work on the technique and the algorithm, we have different targets. So from property to generating a monitor code, which is in Python, or generating C code, or generating VHDL code. So for these different frameworks, we have different targets, right? So anybody interested in using these tools specifically to solve problems with regard to SOC chip verifications, so feel free to contact me. I think I hope you understood something from the talk, right? You have some takeaway from the talk. So thank you, and I'm open to questions.
There we will be having some standards and we have to complain this thing, and whether you check on that with the verification or you do it with as a separate process.
Yeah, I think this is a very good question. Often like when we submit papers, we get the same question. So thanks for
But
asking.
I'm not the reviewer.
So actually at this stage, I think we are basically like validating the schemes, etc. We basically like are in contact with the medical practitioners. So we have collaboration with AIIMS Bhubaneswar. So with regard to the properties to be monitored and so on, like if I take the example of the heart pacemaker closed loop system, right? So what are the timing intervals that the system should typically maintain, all these things. So we, for the for the completeness of the properties being monitored, all these things, we consult the medical practitioners. We try to get some insights, input from them.
Not only in the safe medical this thing, you have other standards to meet when it comes to real-time systems like in defense and all. So
right.
Something like I have heard of DO 254 or something.
Right. So the industrial, various
Standards,
industrial standards. Yeah. So yeah. So the MD and these things. So yeah. So at this, yeah. So at this stage, of course, it's not like at the product level. It's basically like a solution proposal. It's not like at the product level. It's still at the research stage, I would say, right? So then all these things would come in, how we take care of the certification, recertification.
What if the product is targeted to FPGA and not at the silicon level?
Not at the silicon FPGA. Yeah, so we need to see, like how to tackle this, I think.
Thank you.
Thank you. So any other questions? Thanks to Mr. Srinivas. Your thorough exploration of this topic has provided us with valuable insights and its practical usage and implications. I thank you, and I'd welcome Mr. Surinder Sood on the dais to give the plaque to Mr. Srinivas. Thank you. Now coming to the last part of today's event,
is recognizing all the volunteers who have put hard work to make this event a success. So I would call upon Mr. Ayan Datta on the dais to felicitate the volunteers.
Hello, everyone. First of all, thanks for staying back awake and also participating in all the discussions. It's amazing to see the engagement which happened, and thanks to all the speakers. I know, Professor Srini has already come from IIT Bhubaneswar. I traveled all the way, and thank you very much. It was a very good talk. I know I'm between tea and break, but it's very important to recognize all the people who have been working hard from last 3 months to make 2 months to make this event happen. So I would like to call out their name, and I just want your 5 more minutes to encourage them and thank them for all the hard work. So, maybe Kiran, you can call out the names.
Yeah, I'll call upon the names one by one. Please come and collect your certificates and yeah. So Ujjwal, Dhanush,
So all the audio visuals that you see taken care by this guy and Manu. So give a big hand, I think, for him. Also forgot to mention about Ujjwal. He has designed the website and constantly updating the website. Thank you, Ujjwal, for all the effort.
Manu,
Same here. I think all the CAS video which you have seen, Manu and Dhanush has worked on it. Thank you very much, Manu.
Raghavendra,
Our photographer.
Akash, Pujita, Daksh. No, it's not. Daksh, okay.
So before we depart, I think I started with a welcome address, and I just wanted to take this opportunity to thank all of you. Special thanks to our sponsors, Synopsys, who had been, working with us for multiple events. And there's some special mention which shouldn't go out without mentioning. Anushka, she's one of our cast members. Please come. She had been a student member working with us. Now she's working in industry, but still, had been very active. A big hand for her. He had been a very good MC. Thank you very much, Anushka. Thank you very much. Kiran, he had been working with us as an executive committee member, and definitely mentioned the way he had worked. And thanks for all the contribution as an MC. Thank you, Kiran. One person who has worked behind the scene is Surinder Sood. I want you to be here, sir. He is actually posted in UK. He is in Diwali, but he is working with us from last 2 months to make this event happen. So give a big hand for Surinder, who even being working on a deputation in UK is actively working with us. Last but not the least, he's too modest to tell that. Last but not the least, all the executive committee members who are here, for supporting the event, I thank you, Dr. Shalishri, Strobona, Jayesh, Prabhavati ma'am. I think we have Hari. Everybody has been working hard to make this event a success. I thank all of them. This is a team effort which you are seeing. I'm just representing on their behalf, and they all, require a big round of applause to, their work. So this is just the beginning. We want all of you to go back with a lot of good energy, thoughts, and come back with a lot of innovation. We want to make sure that the IPs coming out on verification goes up with publications, patents filed on these areas. So please go back, let this momentum continue so that it translates into something impactful. So with that, I wanted to thank you all. The tea is waiting outside. Please network and connect with them. You want to announce something?
Yeah. all the organizers, execo members, and student volunteers, just stay back for the group photo.
And even if you want to take pictures, please come forward, I mean, for the event. And do give your feedback. I think there are volunteers here. Please pass on your feedback. We can record in video and post it as well. Good, bad, both, right? How we can improve. And at the same time, if you liked it, please post it in LinkedIn with your photographs, tagging the LinkedIn account of IEEE CAS Bangalore chapter. Thank you very much. Have a good evening.